Everyone, welcome to the Space Environment session on plasma and magnetosphere. Our first speaker is Andrew Poppy from Space Sciences Lab of Berkeley, and he'll talk about the lunar paleomagnetosphere fractionation of solar wind minor ion flux. So in the next 10 minutes.
This meeting is being recorded.
Okay, thank you, Dario. I will go ahead and share and get started. So let's see. Okay, just to check, does that come through nicely, Daru?
Yes.
Okay, good. So thank you for joining so early for those of us in the West Coast or in the late afternoon for those of you in Europe. My name is Andrew, and on behalf of myself and my co-authors, Ian Garrick Bethel and Shahab Fatemi, I'm happy to talk about the lunar paleomagnetosphere and the implications this has for fractionation of solar wind minor ion flux to the lunar surface. So the overarching motivation for this work is that we know that lunar soil samples taken from the surface and returned to the lab on Earth by the astronauts record implanted solar wind material. So the cute little cartoon I show on the left is generally to depict outflowing material from the solar wind. Obviously, it's primarily composed of protons, but there is a long list of minor ion species that are also present in the solar wind. Perhaps the most well-known minor ion is solar wind alphas or helium-4, but this extends all the way out in the periodic table, all the way out to xenon, potentially higher. And these elements are actually really remarkably important to study because they are not generated by nucleosynthesis in the sun. They are actually, quote unquote, primordial, and they originate from the protoplanetary disk out of which the sun and the solar system formed. So by measuring these minor trace ion species, we can actually learn about the composition of the protoplanetary disk. As these ions are being emitted from the sun, they're recorded, they're implanted deep into the regolith of the moon. And a lot of research has gone on to looking at variations in different isotopes of these samples, especially as a function of time. So the figure on the right is adapted from a review paper by Rainer Wieler et al. In 2016. And what he showed is that if you take certain ratios, here, for example, argon to krypton or krypton to xenon, and you compare that ratio between different aged samples, between old samples, which are more than 1 billion years old, young samples, which are less than 100 million years old, you can see isotopic variations. So some are enriched in argon versus krypton, some are enriched in krypton versus xenon. And one of the questions is, why might this be? Is it telling us something about the sun's variability as a function of time? That's one possibility. The other possibility, and that's what I'll talk about here, is that the moon is actually playing a little bit of funny business with us, and it's actually modifying these fluxes to some degree just before they're implanted in the surface. So the motivation for this study is to try and understand what role the moon is playing in potentially altering these isotopic ratios from the sun. So we know through really a nice body of research that the moon had a dynamo, and actually that dynamo existed up to approximately 1 billion years ago. So for almost 3/4 of the moon's life, it had some sort of dynamo and global magnetic field. The figure on the left is from a recent paper by Mihani et al. 2020. And what they generally show is that the dynamo existed in a very high field epoch. This is tens to 100 microtesla. That's on the order of the Earth's field. And that was early in the moon's lifetime, about 4 billion to 3.5 billion years ago. Somewhere around 3 billion years ago, this dropped to a more moderate level, about 5 microtesla, that apparently lasted for actually almost half the moon's lifetime, from about 3.5, maybe up to 1 billion years ago. And then finally, after about 1 billion years ago, the dynamo completely shut off and was done. But the implications of this are that actually for most of the moon's lifetime, it had a dynamo, and by extension, it must have had a paleomagnetosphere. So along those ideas, Garrick Bethel et al. In 2019 performed some initial simulations using a hybrid model to look at what the structure of this magnetosphere would look like. It's very reminiscent of what we see at Mercury, but about a factor of 10 higher. Mercury's field is about 0.3 microtesla on average, whereas the moon is thought to be about 5 microtesla in this epoch. But what you can clearly see is that a very well-formed magnetosphere appears. And so what implication does this perhaps have for the inflowing solar wind and how that solar wind is implanted into the lunar soil. So that begs the question, and something we kind of coined magnetospheric fractionation. So fractionation is a general type of process of anytime you get differing responses based on the mass of an isotope. So you can separate isotopes and get different ratios. Here we coined the term magnetospheric fractionation, which not only depends on the mass of the isotope, but actually the charge state, because we're talking about electromagnetic interactions. So the question we posed in this study was, does the charge to mass ratio of all of these minor ions, all of these minor isotopes, actually affect differing rates at which these ions are implanted in the lunar soil? So high charge to mass ratio, these are typically lighter ions like protons or alphas. Are they more likely to be deflected by the bow shock, the magnetosheath of this magnetosphere? Whereas low charge to mass ratio, these are typically heavier ions. Are they able to penetrate a little bit more and get down to the surface? And there you could stretch out this fractionation as a function of mass as well as charge to mass ratio. So the hint here is that, yes, this absolutely does impact the flux of material down to the lunar surface. So to quantify that, we first ran a whole bunch of base simulations for the lunar paleomagnetosphere, first looking at the different strengths of the dynamo and therefore the different strength of the surface magnetic field. So shown here are 8 simulations. The first one on the left is for no paleomagnetic field. This is basically akin to the current day state of the moon. You see there's no structure upstream of the moon, and we see a nice wake in the density behind the moon. That's essentially what's seen today. If we then turn on the paleomagnetic field starting at a fairly low value, only 62 nanotesla or so, and increase it by factors of 2, as we get all the way up to 4 microtesla, you can see a nice suite of growing configurations of the lunar paleomagnetosphere. The closest one we get is about 4 microtesla. This is very close to the estimated value in the middle of the moon's lifetime of about 5 microtesla. So this is generally close. This lower right panel is generally close to what we think the median value for the moon's magnetosphere was for most of its lifetime. So this provides us with a base set of what we think the lunar paleomagnetosphere would look like. And through these background electromagnetic fields that we've then simulated, we actually tracked a large range of heavy minor ion species. So this is everything from alpha particles, which are sort of the lightest heavy ion species, all the way out to ions that essentially replicate the behavior of xenon, which is very heavy at 132 AMU. I show an example here of the different types of structure you get. This is for a single magnetic field strength. This is for 1 microtesla. But now each of these panels is showing you a heavier and heavier minor ion in the solar wind. The general shape of the interaction is the same. We see the bow shock, we see the lobes, we see the dayside cavity carved out. But if you sort of pay attention and look at some of the finer details much closer as you increase in mass, you can see that there is actually changing precipitation to the lunar surface as a function of mass. There's a number of notable features. You can see the striations in the bow shock. That actually has to do with essentially the gyro radius of these ions as they interact with the bow shock. But from these sets of simulations, we then computed the precipitating flux of these ions onto the surface. So if you look closely, for example, you can see flux precipitating in through the cusp regions of these magnetic fields, and trapped radiation-like belt particles that also precipitate to the surface. So from all of these simulations, we have a huge library. We essentially computed the relative flux of different isotopes down to the lunar surface. And that's what's shown here. We show a comparison of the argon to krypton ratios, the krypton to xenon ratios, and the solid black dots are essentially what we've pulled out from the model as a function of magnetic field strength. And the dashed lines are comparing, going back to that first Wheeler et al. Paper, the old lunar ratio and the young lunar ratio. So there's a little bit of isotopic deviation between these. And we can clearly see that just this simple test of running different paleomagnetic field strengths very much changes the isotopic ratios of these well within the range that is actually observed in the samples. So the goal is not necessarily to show that this exact field strength was at the moon, but simply to show that if you did have a paleomagnetosphere, you can torque these isotopic ratios all over the map, and could be one potential explanation for the variations we see in the lunar soil samples. So just to briefly review the key points, we know that the lunar soil records samples from the sun. We know that the moon possessed a paleomagnetosphere up to about 1 billion years ago. We know that this paleomagnetosphere would have led to significant effects on these precipitating ions and would actually have caused some amount of this isotopic fractionation in the soil samples. And all of the details that I very quickly glossed over in that talk are available in a recent paper in the Planetary Science Journal. So if you're curious, you can check that out, or you can send me an email for more questions. So thank you.
All right, very nice. Thank you, Andrew. There's one question from Prabal Saxena in the chat window. And the question is, do you expect to see latitudinal variation in abundance or fractionation based on the models, depending on where the particles may have been also traveled through open field lines?
Yes, absolutely. That's an excellent question. And in the paper, I actually have a couple plots of what the latitudinal precipitation fluxes look like. So you get precipitation concentrated in the cusps. You sometimes get belts of precipitation caused by these sort of trapped particle regions. So the answer is yes, you get very inhomogeneous precipitation on the surface. There's lots more details in the paper, but that's a good point.
And I guess this could also be the diagnostic of the magnetic field.
Yeah, it's dependent on not only the strength, but actually the orientation of the paleopole, which is a whole nother set of simulations to be done. So.
Thank you, Andrew.
Okay.
Okay. Yeah, there are some more questions. I think someone's microphone is off with a timer alert. Yeah. There are some more questions in the chat window. Andrew, I encourage you to answer them in the chat, and we need to move on to the next speaker. It's actually from Shaosui Xu of Space Science Lab, Berkeley. So, Shaosui, are you there, please?
Yes. Hi. I'm Shaosui. I'm a researcher at the Space Science Lab. Let me pull up my slides.
Yeah. And we can continue the discussion in the chat.
Sounds good. Sounds good.
Sure. Thank you.
I hope you can see the slides all right.
Yeah.
Good. So today I'm going to talk about the lunar photoelectron yield inferred from Artemis measurements. And this is me and my lovely co-authors. So just a brief introduction and also motivation. What is photoelectron yield? This is the number of emitted photoelectrons per incoming photons. So this is one of the fundamental properties of solid materials. Here, of course, is a lunar surface. And this quantity is not well constrained for photon energies, about roughly 20 eV. And the main motivation for study this quantity is to a better characterization of the lunar surface charging environment. And then the surface potential we know varies dramatically in different plasma environment, and also in response to solar photon fluxes, which varies a lot through the solar cycle, solar rotation, and also solar flares. Especially during the solar flares or some events, the high energy photons are more bright, and then this high energy photoelectron characterization becomes more important. So we will have a better surface charge model if we have the high energy photo emission yield determined. So that's the main motivation for this study. So I will start with a case study, what the lunar photoelectron looks like, and also especially we make the first report of OJ electrons. So if you look at to the right, this is orbit example. And we focus on these two panels, which are the energy spectrum for parallel and anti-parallel electrons. Especially for this one, we see a distinctive line at roughly 400 to 500 eV. To say it more clearly, if we integrate over this time interval and plot the spectrum for parallel, anti-parallel, and perpendicular separately, you will see this nice peak at 500 for the 500, which is this line here. And this is what we know from theory. These are OJ peaks. What are OJ peaks? These are OJ electrons, which are the photoionization of the inner shell electrons. So they, because of the atomic level processes, this peak actually occur at fixed energies, which is 500 for oxygen atom. So this is a unique feature to unambiguously identify lunar surface photoelectrons. And also, I think this is the first report of oxygen OJ electrons at the moon by Artemis. So this is a case in the magneto tail lobe. We selected 4 other cases too to study the photoelectron. Yeah. So now that we have the photoelectron spectrum, and then this is the equation to calculate the photoelectron spectrum if we have the solar spectrum, the yield, and also the probability function. So both the first two are a function of photon energy, and we can get the photon flux from FISM2, which is a solar spectrum model. And then another quantity we need is this probability function, which characterizes the distribution of electron flux as a function of photon energy beam at a single photon energy. So this is a function that depends on both the electron energy and also photon energy. Assume all these quantities known, we can calculate the yield with a matrix inversion. And to the right, I show a few different probability functions reported in the literature. And then if we follow that equation and use that probability function, these are the derived yields with different probability function and also for selected photoelectron spectrum. So this is a yield against photon energy. And we also plot the photoelectron yield reported in literature, which come from the experiment results, which are the triangle here, which only goes up to roughly 20 eV. So we can see the yield increase rapidly and peak roughly at 15 eV and then drop down. Without doing any more thing, you will kind of assume it just keep dropping. But our calculation are the red and blues because the lunar surface potential is unknown. We have to bound it with high and low values. These are the red and blue lines. But in general, what we can see is that the yield is roughly 1% for high energies and roughly constant changes with altitude. And then the uncertainty is roughly 1 order of magnitude. So it seems everything is fine. But the big thing with this is all the probability function in the literature are assumed. So there's actually no measurements for the probability function at high energies. So that motivates us to do sensitivity study with delta function to test how much things can change with different probability function. So the conceptually to understand the delta function is that, say, if you have a photon with 20 eV, it can produce many 1 eV electrons versus a couple 10 eV electrons. So naturally, when this ratio of electron energy against photon energy is smaller, you expect a higher yield. That's what you see here. These are different levels of this ratio. Now, alternatively, if this ratio is 1, that gives you the lower bound of the yield. So through this sensitivity study, we can infer a lower bound for the yield, roughly 0.1%. But we do see uncertainty over orders of magnitude. And now, of course, in the study, we go into detail, look at different parameters and their impact on the uncertainties. So just to quickly summarize, and we make the first report of Austrian, what did I say? It should be OJ electron observation at the moon by the Artemis spacecraft. And we also infer a lower bound of 10 to the minus 3 in photoelectrons at high energies, but we did discover orders of magnitude uncertainty in yield because the probability function is unknown, which motivate future experiments on lunar sample for better understanding. So yeah, so that's all. And this paper is published in JTR not long ago.
Very nice, thank you.
Thank you.
Yeah, I have a quick question. If you go back to the previous plot, could you explain why high surface potential gives a higher yield versus low surface potential?
That has something to do with the correction to the spacecraft potential. It's just the photoelectron spectrum will be different when you correct for the potential. And actually, this one seems to be showing more clearly. This impact is more obvious for low energies, but at high energies, this correction is negligible. So that's where you see the two are roughly agree.
Okay, thank you. We are good on time, so we'll move on to the next speaker from Robert McDowell of NASA Goddard to talk about radio data from the ROSES NASA lunar payload. Yeah. Robert, I saw you're a co-host. Would you please share your slides? Robert, are you on? So you are unmuted. And also, I guess perhaps you need to stop sharing your slide.
Yeah, there are no slides being shared at this time. Robert, sorry, we're not able to hear you in case you are trying to talk. If this is persistent, we might need to switch over to Michael and then come back to Robert in case he can present later.
Yeah, the button shows he's unmuted, but we cannot hear him. Okay, I guess we can go to Michael Collier first, then come back to Robert. So the title of Michael's talk is the Lunar Environment Heliospheric X-ray Imager, and Michael is from NASA Goddard. So Michael, if you're on, would you please start your talk?
Sure, copy that. I'll go ahead while Bob and Ricky work out the
the sliding
issues there. So can you
Yes.
Obviously, you can hear me. I guess, can you verify that you're seeing slide 1?
Right, in the presentation mode. Very
Okay,
nice.
excellent. Would you like me to proceed?
Yes, please.
Okay, copy that. My name is Mike Collier, and I'm going to talk today about LEXI, the Lunar Environment Heliospheric X-ray Imager, which is a wide field of view soft X-ray imager. Now, LEXI will be one of 10 CLPS, Commercial Lunar Payload Services, instruments hosted by the Firefly Aerospace Blue Ghost Mission 1 vehicle, with an anticipated landing in the second half of 2023 at Mare Crisium. LEXI is led by Principal Investigator Brian Walsh, who is a professor at Boston University, and it includes 6 other institutions, which are shown in the upper right in this slide. LEXI will observe the solar-wind magnetosphere interaction from the surface of the moon to address outstanding problems in heliophysics, such as, for example, the nature of magnetic reconnection. LEXI detects solar wind charge exchange, SWIX for short, soft X-ray emission. In the mid-1990s, the ROSAT spacecraft imaged Comet Yakutaki in soft X-rays. See figure 2A in the upper left. Now, X-rays are usually associated with very hot objects, and comets clearly are not hot, they're balls of ice. Thus, it's quite a surprise, or was quite a surprise at the time, when ROSAT detected unexpectedly large amounts of soft X-ray emission coming from Comet Yakutaki. Now, this mystery was solved by Tom Cravens at the University of Kansas, who's also a member of our LEXI team. Referring to figure 2B in the lower right, high charge state heavy ions in the solar wind, such as oxygen +8, interact with cometary neutral atoms and steal an electron, charge exchange. Afterwards, the heavy ion is in an excited state, and when that excited state relaxes, soft X-rays, X-rays below about 1 keV, are emitted. Solar wind charge exchange occurs not just at comets, but everywhere in the heliosphere that the solar wind encounters neutral gas. At Earth, in particular, the exosphere extends beyond the magnetopause, the boundary at the edge of the magnetosphere, through which all solar wind momentum and energy powering space weather must pass. So the solar wind interaction with Earth creates a soft X-ray signal, as shown in figure 3A in the upper left. Now, at this point, we understand solar wind charge exchange emission well enough to perform accurate simulations. The lower images on this slide, figures 3B and 3C, show simulations of the soft X-ray emission from the solar wind interaction with Earth. We can identify features in the images such as the cusps, which are the bright red in figure 3B. But most importantly for our purposes, we can image the inner boundary of the emission, which is the magnetopause, indicated in figure 3C, and LEXI's target. So to provide just one example of why we would want to image the magnetopause, the process of magnetic reconnection, which rearranges magnetic topology, is the major mode of transferring the energy that drives space weather from the solar wind into the magnetosphere, and it's illustrated by figure 4A. One aspect of magnetic reconnection that we do not fully understand is its temporal nature. That is, does the process occur quickly, slowly, or in bursts. Now, because magnetic reconnection moves the location of the subsolar magnetopause inward, by determining the location of the magnetopause versus time, we can deduce the temporal nature of magnetic reconnection, as shown in figure 4b. Now, the concept of soft X-ray imaging from the surface of the moon goes back over a decade to the vision for space exploration. At that time, NASA funded several concept studies through LSSO, the Lunar Sortie Science Opportunities Program. These are also sometimes referred to as suitcase science packages. At least colloquially, they were referred to as those at the time. And like the Apollo Lunar Surface Experiments Package, or ALSAP, which is shown in figure 5a, astronauts would place instruments, such as an X-ray imager, on the surface of the moon to take measurements. Our original LSSO concept is shown here in figure 5b in the upper right, and figure 5c shows how magnetosheath soft X-ray emission will appear from the surface of the moon. Solar wind charge exchange soft X-ray emission had been observed and has been observed by astrophysical telescopes designed to image distant angularly small objects. Now, for magnetopause imaging, we needed a wide field of view soft X-ray imager, which we developed, and that's shown in figure 6a and 6b. And we flew as a piggyback on the diffuse X-ray emission from the local galaxy, or DXL sounding rocket, led by Massimiliano Galeazzi at the University of Florida. The purpose of the DXL mission was to observe solar wind charge exchange from another source, the interstellar helium focusing cone. The soft X-ray imager prototype was launched from White Sands Missile Range on December 12, 2012, and performed flawlessly in spite of its Black Brant rocket experiencing, quote, serious thrust anomalies, end quote, which resulted in a very rough ride. Because this was the first flight ever in space of a wide field of view soft X-ray imager, our team got an invited article in Review of Scientific Instruments, along with the cover of the journal, which we show in figure 6c. So we are currently refurbishing our soft X-ray imager to go on the Firefly Aerospace Blue Ghost Mission 1. And figures 7a and 7b show the current refurbished instrument. Some enhancements we're making to the LEXI instrument to improve its performance for this lunar application include adding baffles to increase the signal to noise, that's figure 7c, adding a sunshade to eliminate stray light, figure 7d, and adding a cover for dust mitigation, which is figure 7e. In addition, we're reworking much of the electronics to make them more robust. Now, LEXI is one of 10 science and technology instruments on Blue Ghost Mission 1 that will land near Mare Crisium, as shown in figure 7f, in 2023. Now, Mare Crisium is a 550-kilometer diameter crater in the northeast section of the moon that has a large mass con at its center. And there were 3 prior missions to Mare Crisium. These were all former Soviet Union missions. There was Luna 15 in 1969, Luna 23 in 1974, and Luna 24 in 1976. Firefly's Blue Ghost will be the first United States mission to Mare Crisium. In summary then, LEXI, the Lunar Environment Heliospheric X-ray imager, will land on the moon at Mare Crisium as part of the CLPS, the Commercial Lunar Payload Services Program. LEXI is hosted by the Firefly Blue Ghost Mission 1 lander, shown in this figure. And LEXI will observe the solar wind magnetosphere interaction from the surface of the moon to address outstanding problems in heliophysics, such as, for example, the nature of magnetic reconnection. So thank you very much.
Thank you, Michael. That's very nice. We'll have a few seconds for one quick question, maybe. Okay. If not, if you have further questions, please type them into the chat and our speakers can answer them. So,
okay, would you like me to stop sharing then now?
That'd be nice. Thanks.
Okay.
Yeah. Thank you.
Let me do that. There you go.
Okay. Thank you, Michael. And now we have time to go back to Robert's talk. Robert, I think we can see you on your video is on. Can you hear us? And try sharing your screen.
Robert, I believe you are muted on Zoom.
Yeah, we can see your video is on. Oh yeah, I think that's connecting the voice.
Sorry, Bob, it looks like the microphone isn't picking up your voice, although you are unmuted now. Is it possible for you to call into the dial-in number that the room has? And maybe you could throw a thumbs up if that's something we can accommodate. Perfect. Thank you so much.
Yeah. Should we move on to the next speaker? Or wait for Robert? Ashkan, please advise.
We might ask
Leonardo, the next speaker is on.
Yeah, actually, well, yeah. We give him maybe another 10 seconds or so to see if we can just.
Yeah. And would you also set Leonardo Sordo as a co-host to share the screen? I got a message from the speaker. Okay, thank you. Yeah, looks like Robert's working on the connection.
Also, this is Jack Burns. I'm co-author on the paper. I can share Bob's slides if he's having trouble.
Jack, if you don't mind, maybe we can start with, if you want to start, go ahead and do that. I'll make you co-host. And if Bob can connect his audio, he can perhaps take over at some point.
Yeah,
yes, that would be good. Are you?
Yes. Yeah.
Are you seeing my slides now?
Yeah, you can step back. Okay, then the presentation mode. Yeah. All
right. Very good. So I'll try to get started, and Bob hopefully can join. Do the best we could. This talk is about a manifested mission that's going to be on an upcoming CLPS flight that's tentatively scheduled for this next spring. It's called ROLS's, and it's a radio experiment for the lunar surface to investigate the electron sheath. Bill Farrell, Damon Bradley, and others are co-authors. The experiment, which was built by Goddard and recently delivered to Intuitive Machines, who are going to be one of the first of the commercial landers on the moon, is going to have two frequencies, a low band and a high band. And the low band goes to a few tens of kilohertz, and the high band goes up to about 30 megahertz altogether. The resolution is shown here, and on the figure on the right-hand side shows you the extent of the spectrum. So the proposal goal, as I mentioned before, is really to investigate for the first time the photoelectron sheath, the local ionosphere, if you will, that is near the spacecraft. There is some controversy based upon models as to what the interaction between the solar photons and solar wind and the resulting charging of the atmosphere, or charging of the surface, I should say, looks like. So there's some particular models. Andrew Poppy is a principal author on one of these sets of models. So the idea is to try to test through observations these different models of the photoelectron sheath. And one of the ways of doing this is to actually look at the plasma frequency at low frequencies, the electron plasma frequency. Rolls is going to have the ability to be able to sweep through a large range of frequencies, and so can potentially measure the photoelectron density down to a low level. Let me just check to see if Bob has been able to connect yet and can take over the audio. Bob, have you dialed in?
He is not, but we're working on it.
Okay, let me keep going. As soon as he does, I want to turn this over to him. So here's some data from the WinWave spacecraft from a few years back, and showing this effect of the plasma frequency and being able to do, if you will, a kind of sounding of the local lunar ionosphere. In addition, there are a number of other goals associated with this mission, and I think they're illustrated pretty well here by this wonderful plot, once again from the WAVES instrument on the WIN spacecraft, and this is data when it's its current location at Earth Sun L1. You can see, for example, at the lower frequencies, the AKR coming from the Earth, and this mission being tentatively on the near side, some opportunity to do additional measurements. There's lots of RFI coming from the Earth, and we expect to characterize that. We're hoping for a type 2, type 3 solar burst. There's also the Jupiter. So lots of sources of strong radio emission. One of the things we're looking to do here is to also characterize, update the RFI. Here's another look at a so-called waterfall plot. This is frequency versus time. And all of these stripes that you're seeing going across here above a megahertz are due to RFI coming from the Earth. This is a really good illustration of why we want to go to the far side of the moon to ultimately to do low frequency radio emission. But we'd like to be able to characterize this better and look for potential holes that might exist in this spectrum, and also be able to use a more sophisticated RFI extraction to characterize in detail the galaxy, because the galaxy is going to be a strong foreground for cosmological experiments that we'll be doing from the far side in a few years hence. An additional goal is possibility of dust detection. As was illustrated by the Cassini spacecraft, that these radio antennas are potentially wonderful dust cloud detectors, not individual particles. We don't have that kind of resolution, but clouds of dust which impact and ionize and potentially are detectable. So that is another one of the goals. So let me just put up the summary slide here. And again, if Bob can join us to help field questions, we can do that. But in the meantime, we're very excited that Rolls is going to be the first NASA-funded radio science experiment for the surface of the moon. Has all of these goals that I've mentioned before, and we're looking forward to the launch by spring of this next year. So let me stop there.
Thank you, Jack. We have about 2 to 3 minutes for Q&A for this time slot.
I can do my best to try to answer questions, but Bob is certainly more on the heliophysics side as the expert. And Andrew might have a couple of things to say too. He's very expert and having modeled a lot of these kinds of interaction. So
I'm certainly looking forward to the measurements, that's for sure.
Yeah, so Andrew, I think this is exciting because we have an opportunity to do this measurement on the near side and then follow up with Lucy a few years from now to do a comparable set of measurements on the far side. And because the two are very different, and particularly day-night observations too, that we might have with Lucy. So this could be an exciting advance. I don't see Bill Farrell on because Bill also has been involved in thinking about these issues, particularly with respect to charging of the surface and maybe the effects on astronauts on the surface. I don't know, Andrew, if you might be able to comment on any of that.
Well, I think both the Rolls and the Lucy investigations on the two different CLIPS landers will give us some nice ground truth about sort of the baseline state of the near surface photoelectron sheath and any variability. It's worth noting that both of these missions will land on the lunar surface close to or at solar maximum, which is when all kinds of interesting things happen. So fingers crossed for interesting events, but I think that'll provide some nice ground truth data to compare to some of these models, absolutely.
So we'll have to see also if we're going to be lucky as to whether or not there will be a type 2, type 3 solar burst associated with CME. We're moving towards solar maximum, but not there yet. We're still a few years away. And it would be nice to be able to have that recorded event from the surface as well.
Jack, could you comment on when it's deployed, how far away is the instrument from the lander?
The instrument is right on the lander.
Right on the lander.
Yeah, it's so going back to that cartoon picture that I showed earlier. There's two sets of dipoles, one here in blue and another set that's perpendicular at 1 meter above the surface, and then the spectrometer, the radio spectrometer, is inside and has somewhat of shielding from the heat of the day.
Thanks. We have a few seconds left to transition into the next talk. I guess I'll hand it over to my co-chair, Andrew.
All right, thanks, Daru. Thanks, Jack, if you don't mind ending your sharing.
I will, thank you.
And our next talk will be by Leonardo Cerdo. Leonardo, if you could go ahead and share your slides in preparation for your talk.
Sure. Thank you, Andrew. Good morning and good afternoon, everyone. So let me select my screen. I hope you can see my screen right.
Yes, yes, thank you. Well, it's,
Yeah,
if you
it's good.
swap, yeah, there we go. Perfect. Okay, Leonardo, please take it away.
All right, so just, there you go. So yes, so my name is Leonardo Surdo, and I work for the Human Spaceflight and Robotic Exploration Program Directorate at the European Space Agency. And this presentation will be about the European Space Agency's contributions into radiation research at Gateway. And contributions to this presentation are from other colleagues from the European Space Agency, as you read there, as well as from the Japanese Aerospace Exploration Agency, given JAXA is providing and contributing instruments to the payloads that we are currently pursuing for the Gateway station. So this slide is just to give an overview of what the European Space Agency's human spaceflight and robotic exploration mission roadmaps looks like. So at the moment you can see that we are in phase 0, where we are continuing research and testing on board the International Space Station in the low Earth orbit, and we are going to move as of this decade to the lunar vicinity. And in this we are currently collaborating with NASA, CSA and JAXA into assembling the Gateway lunar station. And then that marks phase 1, and then from phase 1 we will build up also capabilities for entering into phase 2. I don't know why it's moving on without any clicking, but phase 2, which entails the robotic exploration of Mars in preparation of future human space exploration missions. So we decided to contribute to the so-called early phase of Gateway utilization with radiation payloads. Why? Because we are expanding the human presence beyond the low Earth orbit, and the Gateway is going to be there. And so still we want to address some of the risks that human spaceflight has when moving beyond the low Earth orbit. And radiation, of course, is one of the inevitable and dominant features which are relevant to not only crew health and safety, but also overall to mission success, if we also consider the impacts that radiation has also on the electronics. Of course, the energies and spectra of ionizing radiation in the deep space environment is different from what we are currently experiencing on board the ISS with the low Earth orbit space radiation environment. So we are keen into into mapping the radiation environment at Gateway Station destination, and so be able to compare also what kind of radiation environments we will find there with respect to what we are currently measuring with also other space missions. So ESA has decided to contribute to radiation research in order to determine the radiation environment outside of Earth's magnetosphere, compare measurements at different locations and times with the same instrumentations in order to achieve cross-calibration and accurate spectral reconstruction. And all this and all the data that we will be collecting from the Gateway payloads will enable us to determine the health risk for astronauts and validate and improve existing panel and radiation belt models, and I will explain why. So all this is because ESA wants to prepare for and ensure safe astronauts mission. And in this sense, we want to improve space weather forecast and nowcasting capabilities, as well as we want to understand countermeasures against space radiation through shielding. As I was saying, ESA has a long heritage of radiation research using different platforms. On the ISS, we are using currently different platforms. For example, the DOSIS 3D experiment that is mapping radiation inside the Columbus module. and we also performed experiments using the Matryoshka payload, looking at radiation dose absorbed by a mannequin with analog of human tissues. Also, we are running a ground-based facility program for radiation called the IBER program, which stands for Investigation into the Biological Effects of Radiation. And then we are running other ESA missions with radiation instruments, for example, the Herschel, Joby-B, Planck, Integral, Rosetta, and other future Earth orbiting and interplanetary missions where we are focused to measure radiations at those different space locations. So for the early phase of gateway utilization, the ESA research is mainly represented by two payloads. These are the ERSA external radiation sensor array and the IDA internal dosimeter array. These two payloads are planned to be launched with the first two elements of the gateway, which are the power and propulsion element, also known as PPE, and the Halo habitation module, which will be flown in 2024 as currently scheduled. So for the European Radiation Sensor Array, this is an overview of what this payload will consist of. As you can see, there are several science instruments on one single platform, which will be externally mounted on the power and propulsion element. And these instruments consist of two ESA European active dosimeter boards, SRAM, ICARNG, and GRM. We will also have two Medipix units and two magnetometers. The science objectives of the ERSA payload are to measure long-term the radiation environment outside and inside the Earth's magnetosphere, explore concepts for real-time radiation alerts, operational space weather services, magnetosphere radiation belt modeling. The ultimate goal is to support the generation of models for near real-time radiation warning on board gateway for crew safety and for modeling inputs into shielding propagation and radiobiological effective dose equivalent calculations in order to better prepare or best prepare for future human exploration missions beyond the moon and forward to Mars. I was mentioning that not only we will map the radiation environment at gateway destination in the gateway lunar orbit, but also we will be able to measure the radiation environment across the Van Allen belts, because the power and propulsion element and the Halo module in which the ERSA payload will be flying will have a low transit across the Van Allen radiation belt, so there will be an opportunity to improve radiation belt modeling with measurements performed also during this transit. The internal dosimeter array instead is a payload which instead will be located within the Halo module, the habitation module of the gateway, and will consist of one European active dosimeter mobile unit, one treacle detector unit, one Medipix, and then one pedals and one D-space dosimeters from our colleagues at JAXA. As you can see, most of them, they are active dosimeters, but the pedals, which is a passive dosimeter provided by the colleagues at JAXA as an internal control to the active dosimeters during their mission. All these instruments will be grouped together into one payload called IDA, and they will all be controlled by a central electronic unit, which will provide structural power and data interface between the instruments and the gateway. The IDA science objectives are to improve radiation physics models for cancer, radiation-induced aging, as well as cardiovascular and central nervous system effects, supporting crew risk assessment for deep space exploration missions. The data coming from IDA will help refine radiation transport models, evaluate radiation shielding and spallation product generation by the gateway structure, and study radiation effects on electronics in deep space as well. Thanks to IDA and the fact that IDA also consists of instruments which are common to the ERSA outside external payload, we will be able to compare measurements from inside and outside of the gateway. And also with IDA, we are going to acquire data during the transit phase of the first two elements of the gateway to its final orbital destination. Even during uncrewed periods, ERSA and IDA will be able to measure radiation and downlink the data for scientific utilization by the scientific community. It's the ERSA and IDA payloads are a contribution from ESA in collaboration also with NASA, which is currently pursuing also a sister payload on the first two elements of Gateway, which is called Hermes. And together with the Hermes NASA experts and selected science teams, we are going to have complementary objectives and instrumentation shared, as well as the data. And in particular, a radiation and space weather working group with representatives from NASA, ESA, CSA, and JAXA is currently meeting already twice monthly to address joint science for these payloads, and we will extend the participation to this working group also to competed and selected the scientists for making use of the ERSA and IDA payloads. We are currently also elaborating data policies and solicitations to compete the scientific community across the across the countries of the partner agencies to the Gateway program. And what we are currently pursuing is a data policy which provides no prior access prior access rights to the data, but all the data will be freely available to all the scientific community for them to make for them to analyze, to use them and analyze them. But for sure, the competent scientists who will be selected will have the capability to interact and interface with both the Gateway program and the selected teams from the Hermes NASA side. So please stay tuned. The ERSA and IDA announcement of opportunity will be released soon, tentatively towards the end of August. And what we are looking for is an international collaboration between the scientists coming from countries of the partner space agencies to the Gateway program, such that we can have a multilateral international endeavor in effort in making use of the ERSA and IDA data from the Gateway. I think that was it from my side. Thank you for listening.
Okay, thank you, Leonardo. We have time for one quick question if anybody wants to type something in the chat. Okay, we also have time during the discussion after the end of our session. So thank you, Leonardo. If you would mind stop sharing. And Fatima, if you would please bring up your slides. Our next speaker will be Fatima Ramanifard, who will talk about hysteresis in the galactic cosmic ray variation and implications for future solar activity. Perfect. Okay, we can see your slides. So please take it away, Fatima.
Hello all, I'm Fatima and I'm a research scientist at the UNH Space Center. My primary focus of research is the effects of solar variations on our space environment, more specifically as a creator, LRO, and leader SSERVI team member. I am interested in the GCR's radiation and how it limits crewed space missions due to the recent decline in solar activity. This study has been submitted to Space Weather, and here you can see the name of my co-authors. The flux of GCRs is constant at the interstellar medium. Inside the heliosphere, GCRs are modulated by the heliospheric magnetic field, HMF. The flux of GCRs reaches its maximum during solar minimum when HMF is too weak to modulate them, and the modulation potential is defined as the energy lost to GCRs as they travel from the edge of the heliosphere to the inner heliosphere. It can be used to describe the interaction between the GCRs and the HMF or the solar activity. In a recent paper in 2020, Rahmanifard et al. Paper, we investigated the correlation between the modulation potential from crater, as you can see the plot here, with solar wind parameters. Here, phi is the modulation potential based on crater data. V is the solar wind speed from Owens et al. 2017 paper, and B is the intensity of the heliospheric magnetic field from our 2017 model. As you can see here, we use a color code that darker data points are associated with the beginning of the solar cycle. And as we proceed in time, the data points become lighter. So you can see the hysteretic behavior in this correlation, which motivated us to further investigate these correlations. While crater data only covers cycle 24, we can extend our analysis to previous cycles using the results from Badwar-O'Neill 2014 model. So we get the modulation potential from this model, and we use again our model and Owens et al. Model to get the solar wind parameters. And we extend our analysis back to the previous 24 solar cycles. You can see in this figure and in the table, we have separately shown these trends that we have observed in these correlation diagrams for even and odd cycles. We are actually looking for trends that could be used in the prediction of future solar cycles. So in the first row, you can see a steep increase. And again, we use the same color code. We use darker data points for the beginning of the cycle, and they become lighter as we proceed. So in the first row, we can see a steep increase in the first half of the cycle and a more gradual decrease in the second half. Is indicative of a weaker next cycle. The opposite trend is shown in the second row, where a more gentle increase in the first half and a sharper decrease in the second half represents a stronger next cycle. When the difference between the slopes of the two halves aren't that significant, it leaves the next cycle inconclusive. As you can see in the table, we show the schematic figure of these trends along with the list of cycles that represent these trends. Among the 11 cycles for which the diagram, the shape of the diagrams are conclusive, we can successfully predict whether the next cycle is weaker or stronger for 9 cycles. There is a well-known correlation between the minimum of solar activity and the subsequent maximum solar activity. Here we have shown this correlation with Bmin and Bmax. Again, B is the intensity of the heliospheric magnetic field. And you can see we show a fairly good correlation here. But what's new in this, and this has been studied in previous several studies. Jody Wilson also has a poster. It was actually, his poster was yesterday, where he showed a remarkable correlation between the amplitude of solar cycles and their previous minimum solar activity between the sunspot numbers. And he actually in his study, he shows like a significant improvement to compared to previous studies. But what we have here is in terms of the heliospheric magnetic field, and what we show in addition to the previously known correlation is that we show these data points with the blue X that are associated with our predicted weaker cycles. And we see that they mostly fall below the correlation line. The red X shows cycles that we predict to have a stronger next cycle, and they are located above the line. So this suggests that these correlation plots reveal a physical effect in addition to the correlation between the amplitude of cycles and minimum solar activity observed before the cycle. So furthermore, the correlation diagrams in this study, together with this correlation, Bmin and Bmax correlation for the inconclusive cycles. The inconclusive cycles here are shown with the gray data points, and you see that they show a much stronger correlation after removing the data points that are marked with the red and blue X. We see a much stronger correlation. So this correlation for the inconclusive cycles, along with the correlation diagrams that we presented earlier for cycles that actually predict a stronger or weaker next cycle, together form a tool to predict future solar cycles during the ending phases of the current cycle. Based on this analysis, we predict cycle 25 to be as weak as or weaker than cycle 24. This might suggest that the sun has entered a secular minimum, which based on historical records might stay for another 2 solar cycles, cycles 25 and 26. This means that while solar maxima are known to be safer from GCRs, the next lunar mission will encounter higher GCR fluxes than did the Apollo missions. And I finished that here. I'll be happy to answer any questions.
Okay, thank you, Fatima. If anyone has questions, please type them in the chat. For Fatima, we'll give it a minute or so for people to type if they have a question.
Okay, do you want me to stop sharing then?
Just hold on for a moment in case anybody has a question.
Okay.
Okay, I'm not seeing any questions, and we can always return to it during the discussion. So thank you, Fatima. If you don't mind ending your sharing, I appreciate it. Our last talk of the session is a lightning talk. This will be given by Faris Almatouk. And the title of the talk is Utilizing Hexagonal Boron Nitride and Graphene Field Effect Transistors for Neutron Dosimetry. So Faris, if you could please go ahead and share your screen. And start whenever you're ready. Okay.
Great. A graduate student from Georgia Tech. In our study, basically, it's about the idea of utilizing hexagonal boron nitride and graphene field effect transistor to fabricate a neutron dosimeter that can ultimately be integrated into spacesuits in the future. So the boron nitride layer would be transferred at the top of the graphene field effect transistor. Of course, we're choosing a boron-containing layer since boron has a significant thermal neutron capture cross-section. And for that reason, we're growing monoisotopic HBN in our lab using a metal flux method, and the crystal we're getting is in a millimeters in size. Also, to check the quality of those crystals, we're doing characterization measurements, including Raman as well as XPS, to confirm the quality, and actually the values and the peak positions as well as the peak widths are really consistent to very good quality results that is previously mentioned in literature. So our next step, we've already grown the HBN crystals. Our next step is to transfer it to the graphene field effect transistor and then irradiate it with a 2.5 MeV neutrons using a DD neutron generator in Georgia Tech. And so basically our measurement would be resistance measurement. So once the prototype is irradiated with neutrons, real-time measurements, resistance measurements will be done to check the performance of the prototype. And that's about it. I'll be happy to talk more about this study and my poster today, which I believe will take place in about 2 hours, and hope to see you there. Thank you.
Okay, thank you, Faris. And I encourage everyone to go stop by the posters, including Faris's poster and any others that are of interest to all of you. So at this point, we have some open time for discussion. This is discussion over any of the previous talks or related subjects, if anyone wants to quiz an expert in the room. I can actually go ahead and start. Bill Patterson put in a question for Fatima in the chat. So Fatima, Bill asks, and I believe this is, are you aware of predictions for solar cycle 25 duration as well as the timing of the peak? And could you comment on that based on your predictive studies?
Yes. There are predictions, several predictions that are all over the map, but we've had the solar cycle 25 prediction panel, and they actually I guess it was almost 2 years ago now. Wow, time flies. So yeah, they predicted cycle 25 to be comparable to cycle 24, and I guess they. I should look for the exact amounts and values, but I guess their prediction was like the maximum would be in the year 2024. And they expected cycle 24 to end in 2020. So based on their prediction, we are already in the cycle 25, which I guess we are. That's their prediction. So they predicted somewhere around. I should look for the exact values, but they expected it to be comparable to cycle 24. So based on that, our results are in line with what they got.
Yeah, I'm curious because I know that the sunspots for cycle 25 have shown up, and that's true. I'm wondering if perhaps you know. If even the very beginning part of solar cycle 25 matches any of the predictions. It's obviously very early, but could you comment on whether the first year or so of solar cycle 25 is playing out as we might think?
I think Jody is actually following the sunspots much closer than I do, but it seems like the increase isn't like very sharp. So it seems like from what we see now, we probably won't have like a sharp increase or ending to in a strong peak.
Sure. Well, I happen to know that one of my colleagues works on MAVEN, and they were alerted to a big space weather event that I think is going to strike Mars either today or tomorrow. So it is true, the sun is waking up, which is nice to see. Hopefully there's some more interesting science. So yeah, so we are otherwise generally open for any discussion or questions. I think the best way is if people drop questions in the group chat and you put a little Q, and if it's for a particular speaker, you can identify them. But feel free to take a minute or so and brainstorm clever questions to any of the colleagues that are here in the virtual room.
Indeed, Andrew, you have a question in the chat window from Shao Sui earlier.
I do.
Sorry.
Yeah.
If I could just say a quick sentence. So their prediction was sunspot numbers between 95 to 130. sunspot numbers. And from what I know from Jody, is based on his correlation, next cycle would be around 100, and based on like the latest observed sunspot numbers, the next peak would be like 140 sunspot numbers. So we see a very close match between.
Okay, well, time will tell in the next few years. It'll be exciting to watch. So, sorry, Daru, you said I had a question?
Sure, yeah, it's from Shaoxi about what causes the downturn in the fractionation curve at about 1 microtesla.
Right, so to recall a plot that was 8 talks ago, one of the things I was showing was the ratios between argon and krypton and xenon that were implanted in the solar wind. And it was true that those curves were not, perfectly declining or perfectly increasing. There were some odd bumps. The interesting reasons behind this are actually a couple-fold. One is that these ratios, obviously you're dividing one thing by another thing, and each of those ions have different charge to mass ratios. So argon has a little bit higher charge to mass ratio because it's a lighter species than krypton is. And what that means is that those two ions are sort of interacting with the different strength paleomagnetic fields in different ways. What we generally see in the model is that for very low paleomagnetic field strengths, we saw that the heaviest ions can basically just penetrate right through the bow shock right down to the surface, whereas the lighter ions were sort of diverted around. What we noticed after that, however, was once you got to a critical strength that I think was around, I think it was 500 nanotesla or a microtesla for the magnetic field strength, that nearly all the ions were shielded from sort of direct precipitation onto the day side of the moon. And what started to happen was the cusp precipitation became much more important, as well as particles that had been trapped sort of in a radiation belt-like region, a quasi-trapped region, and then were sort of slowly grazing across the surface of the moon all the way around. And the reason of these sort of somewhat hard to understand bumps in the fractionation curves is because these different effects, the direct precipitation or the cusp precipitation or the radiation belt precipitation, those all sort of appear at different magnetic field strengths for different ion species. And so the argon curve is doing one thing as a function of magnetic field, and the krypton is maybe slightly offset. So if I'm taking ratios of them, the ratio can actually go to fairly high values and then go to fairly low values because the underlying ion behavior is actually somewhat complex and due to a number of different features. We actually ran, I think it was 8 paleomagnetic field strengths and 9 ions. So I have this giant chart of all the different types of interactions. And it is somewhat difficult to summarize in a single curve. There is actually a lot of dynamics going on beneath the surface. So it is obviously dependent on the paleomagnetic field strength and the direction that we choose for the paleopole. And a lot of this has to sort of be further explored, but it does at the end of the day, I think, point to the fact that these interactions are actually fairly complex and is definitely something that needs to be taken into account when we're trying to interpret this sort of lunar soil sample record. So,
yeah, thank you. Yeah. I have a follow-on question. If you pull up your plot, that'll be easier to describe. And I can state, I was wondering, what is your numerical solver? Is that electrostatic with a B field or purely electromagnetic?
This is it's a 3-dimensional electromagnetic hybrid model. So the way it works is that we follow individual ions as macroparticles, sort of similar to the particle and cell method, or actually it's identical to the particle and cell method for the ions. The electrons are considered to be a fluid. So what that limits you is that you have to work inside of a regime where the physics that you're interested in is greater than the electron inertial length scales, but typically smaller than the ion inertial length scales. And it turns out that the moon's paleomagnetosphere, and actually the moon's interaction, even without a paleomagnetosphere, is right in this sweet spot where the scale lengths are larger than the electrons' scale lengths, but smaller than typical ion scale lengths. And so the hybrid model has been well tested. It was developed by my colleague Shahab Fatemi, who's now in Sweden. And we've applied it to Mercury, the moon, asteroids, all kinds of things. And so it does solve electromagnetically. It is self-consistent in that sense for the fields. And it actually has a lot of power and a lot of ability to describe a lot of these. It, for example, does not have the ability to describe something as large as the Earth's magnetosphere. That is really somewhere where you need an MHD model because you're looking at far larger than ion scale. You can do it with a hybrid. It'll just take a really, really, really long time to process.
So it's a kinetic ion, fluid electron, electromagnetic.
Correct, absolutely.
And how did you initialize the dynamo of within the moon? Just a magnetic dipole?
Yep, just a simple magnetic dipole. We typically oriented it such that it's aligned with the spin axis of the moon. It doesn't necessarily have to be that way, but to run the first set of simulations, that's sort of the default assumption. There is some laboratory measurements of what's called the paleopole orientation. So was the pole perfectly aligned with the spin? Was it offset? In which case it would sort of rotate around on a lunar day. Those are all possibilities, and they are deserving of more research and more modeling to try and understand what the effect of that would be on these isotopic precipitation ratios. So.
Yeah, for all the charts you presented, they have the same orientation or inclination of the dipole.
Yeah, this is often the challenge with modeling, especially somewhere where you don't necessarily have a lot of constraints, is you can explore a lot of phase space, but you have to pick something small and manageable to get started.
Right. Yeah. Thanks. Thank you, Andrew. Very interesting.
So yeah, again, I'd encourage folks, if you have questions, to drop them in the chat. I imagine we'll let it go in, let's say, another couple minutes, and if no new questions come up, I think we can release people to take a small break before going back to the plenary. But I do want to make sure everybody has a chance to quiz your colleagues as much as you wish. So.
Yeah. And some of our talks in this session are connected with the posters. So if you're interested, you can also go to the poster session, see the posters. Yeah. Maybe people are forming questions, and if not, we'll have a 15-minute break before the plenary.
Thank you all. Bye.
So I think Daru, we can perhaps close the session here.
Yeah.
But I wanted to thank all of our speakers again, and everyone from multiple continents from calling in. Bright and early or late in the evening, it's much appreciated that everybody can come together, and hopefully we can all see one another in person at some future date, hopefully not too far from now. But I think until then, it's wonderful to see everyone virtually and connect and learn about all kinds of good science. I encourage you all to stop by the posters with GatherTown. It's a neat experience to walk your little person around the poster hall and interact with people. So I encourage you to check it out. And other than that, Daru, I don't know if you have any other closing thoughts.
Yeah, I think it's good.
Okay. All right, Ashkan, I think if you can gracefully end this session, I think we will be good. And I see Ashkan has put a plenary session Zoom link in the chat. So if you wanted to jump over to there in preparation for the next set of talks, feel free to go ahead. So.
Yeah, it will start at 45 past the hour,
okay.
Whichever continent you are.
Yes, so, okay, all right. Thank you, Daru. Thank you everyone again. And hopefully see you in some other Zoom chat soon.
Right. Yeah.
All right.
Bye.
Talk to you later.
All right.
Bye-bye.
Thanks, everybody. Bye.
Bye.
Hi, everyone. Welcome to parallel session 3, surface composition and sample analysis. My name is Tim Glotch. I'm at Stony Brook University. Let my co-chair introduce himself.
Hi, everyone. Yes, I'm John Penny-Fisher at the University of Manchester.
We just have a few announcements before we begin. Just want to welcome everyone. For this session, talks will be 8 minutes long with 2 minutes for questions. Behind either my head or John's head, you'll see a timer. And so for speakers, if you want, you can pin the video screen to see the timer while you share your own screen. And we'll give you verbal reminders at 6 and 8 minutes. The last talks of this session are student poster lightning round talks that are 2 minutes each. We'll also have a video timer for those. We'll provide you with a verbal reminder at 1 minute and 30 seconds. We'll also have a longer discussion period after all the talks have been made, so please stick around for this discussion opportunity. And for other participants who are not speaking, please stay muted and keep your video cameras off unless you're called on by a session chair. If at some point you'd like to pose a question to one of the speakers in the chat, please preface your question with a Q to highlight these for John and I so we can keep track of the questions. And make sure you keep the discussion inclusive and constructive in accordance with the NESF ELS Code of Conduct. Finally, please respect the intellectual property rights of each presenter by not sharing screenshots of their work without their permission. And participants should also feel free to close the chat window if it's distracting, and John or I will convey any important information or announcements verbally. With that, I would like to introduce the first speaker, Marjolein Dater, and her talk is titled Experimental Data on Partial Melting of an Ilmenite-Bearing Cumulate Layer on the Moon. Are you there?
I think you're muted.
Oh, am I muted?
I can hear you now.
Marjolein, it looks like you might have some bandwidth issues right now. I've tried turning off the webcam, but if possible, is there a way for you to dial into the phone line instead of computer audio?
You can't hear me?
I think you're coming in and out. Ashkan suggested maybe you can call in to the phone line to speak, if that works. We can see your slides, but we cannot hear you.
Now?
I can hear you, yes.
Okay, perfect. This works. I'm so sorry.
Okay. I'm starting the timer now.
Okay, thank you. So hi everyone, this presentation is about my master's thesis at VU Amsterdam on experimental data on partial melting of an ilmenite-bearing cumulate layer in the moon. So this session is of course about surface composition, and while the title may give the idea that my thesis doesn't really fit in, there is a link to the titanium-rich surface basalts found both in Apollo samples and by remote sensing of volcanic deposits on the surface. These titanium-rich samples are thought to be related to a titanium-rich source in the mantle of the moon, and my thesis is about such a potential source. To make rocks rich in titanium, we first have to look at the way the moon solidified from a global lunar magma ocean. As shown in these sketches by Lin et al., upon cooling of the lunar magma ocean, mineral cumulates form different layers. Only the layers that form last, when the ocean is almost all solidified, contain the mineral ilmenite, which is the main host of titanium in the moon. This ilmenite-bearing cumulate layer is a thin one in orange here. Because there's so much titanium and iron in this layer, it's very dense, and it will sink into the already formed cumulates below, leading to a so-called overturn of the mantle. Melting of the titanium-rich cumulates could lead to the forming of a dense melt reservoir at the core mantle boundary that is seen in lunar seismology. And it could also lead to the forming of the titanium-rich surface basalts. But not too much is known about the melting behavior of this ilmenite-bearing cumulates at different depths in the moon. This study aimed to put experimental constraints on the amount of partial melt at certain pressures and temperatures. How this was done is I made my own ilmenite-bearing cumulate composition in the lab on the basis of the magma ocean crystallization work done before in Amsterdam. I loaded my synthetic sample in a very small 4mm sized graphite buckets and assembly and put it in a piston cylinder press to pressures of 1, 2, and 3 GPa, which correspond to depths in the moon of around 200 kilometers for 1 GPa, 400 kilometers for 2 GPa, and 700 kilometers for 3 GPa. The temperatures ranged from 1100 to 1400 degrees Celsius. After the experiments, samples were cut and polished and analyzed at the electron microprobe in Utrecht. In backscatter electron images, we could identify the different phases present in each experiment, and their chemical compositions could be measured. Using mass balance equations, the abundance of each phase could then be calculated. The images were also analyzed with a machine learning pixel classification program that was employed to assign individual pixels in the microscope images to different phases. Phase proportions were also obtained from this approach and then compared with the chemical mass balance approach. These are the phases found in each of the 15 experiments, spreading in a range of pressures, here on the x-axis, and temperatures on the y-axis. In terms of minerals, ilmenite is present in almost all experiments, here in green, with rutile only stable at higher pressures. You can see it in pink. Ansatite and orthopyroxene is present throughout, and pigeonite and clinopyroxene is present at higher temperatures, the orange one. And augite, a clinopyroxene with more calcium than pigeonite, is present at lower temperatures. Quartz is also present at low temperatures. Melt was found in almost all experiments, meaning that ilmenite-bearing cumulates would produce melts at all the temperatures given here on the y-axis. The melt percentage varies with different pressures and temperatures, as shown here. This graph has the melt percentage on the y-axis and temperature on the x-axis. It's quite a busy diagram, so I'll break it down. The different pressures.
We're not seeing your diagram.
You don't see a diagram?
No. We're still seeing the backscatter electron image.
Oh, no.
I think there's a delay between when she is advancing the slides and when we're
seeing. Oh, I'm so sorry. Okay.
Now we see the colored version, so it's catching up.
Okay. So you didn't see the one with the minerals at all either? Okay.
Right now we see the color-coded backscattered image.
Okay.
Or at least I do. Okay. now we see the results: melt percent versus temperature and various pressures.
Just progress from there. Then maybe afterwards I can show it again if we still have some time. I'm so sorry, guys. So this is the melt percent on the y-axis and the temperature on the x-axis. I hope we all see that now. So the different pressures are represented by different colors, and the brighter colors are obtained from the chemical mass balance approach, and the duller colors are from image analysis. And as you can see, the general trend is that higher temperatures give more melt, and also lower pressures give more melt. But you can see that there are several deviations from this, particularly for the 1300 degrees Celsius experiments. We found very little mineral at 1 GPa and 1400 degrees, so we expect to be close to the liquidus temperature there. And we found almost no melt at 3 GPa between 1100 and 1150 degrees, and at 2 GPa at 1200 degrees, so we expect to be close to the solidus there. In general, the image analysis and mass balance approaches are in reasonable agreement, but we favor the mass balance approach because different cuts through the experiments could yield different percentages in the image analysis, while the mass balance is calculated for the entire sample. So I'm moving on to the next slide, so I hope it catches up with you guys. What does this mean? First of all, in many numerical models of the evolution of the interior of the moon, people use the solidus of terrestrial mantle peridotite as a measure for whether melting takes place. The peridotite melting curve. Oh, I'm so sorry. What did you say?
4 minutes left.
Yeah, thank you. So I hope you see the next slide now with the discussion, where the peridotite melting curve is sketched here. I hope you can see. The ilmenite-bearing cumulates, as you can see, melt much more easily than peridotite. Also, the study of Malik et al. From 2019, using a very similar approach to ours, found that as well. Our solidus temperature seems to be even a bit lower than Malik's work. In other words, the cumulus could produce quite a lot of magma in the moon, more than was previously thought. So in conclusion, we found that the solidus of the ilmenite-bearing cumulates to be at 1200 degrees at 2 GPa and between 1100 and 1150 degrees at 3 GPa. This means there is more melt in the moon's mantle than we previously thought. Future studies could perform similar experiments to this thesis at core mantle boundary conditions to explore the composition and density of the magma there. Furthermore, the results from this thesis can be incorporated in thermal models of the moon, and this will give us a better insight in the lunar interior. And lastly, the chemistry of the melt found with my experiments could be linked to the composition of the titanium-rich surface deposits. And I have a last slide if it's allowed. As I said before, this was my master thesis, and now I'm looking for a PhD opportunity. So if you know any in the field of planetary science, you can contact me here, and you can see my CV with the QR code if you want. Are there any questions?
That was wonderful. Thank you so much. And thank you for working through those technical difficulties. You did a wonderful job.
I'm sorry.
No, it's not your fault at all. Are there any questions for Marjolaine? There's a question from Catherine Joy. What's the significance of the large amounts of rutile in your experiments?
Yes, I looked into that because I was wondering if you have more rutile, you would have less ilmenite because they both contain titanium. But that doesn't seem to be the case. It just is like an extra. I did find that if there is more rutile, there's less titanium left in the melt, so it might be less dense, therefore. If that answers your question a bit.
Let's suggest if there are any other questions, we can have those in the chat. And Marjolaine, you can monitor the chat, see if any questions come up. But thank you so much.
Yes, thanks so much.
We'll move on to the next speaker, which is my co-chair.
Indeed, thank you very much. So let me just share my screen and hopefully, whoops, there are no issues. Okay, can everyone see my slides okay?
Yes, we can.
Fantastic. Oh, sorry. Brilliant. So thank you all very much for tuning in. I've got the fan on in the background, so if it's cutting in the mic, do holler and I can just adjust that. So yes, I'm going to talk a little bit about the oft under-discussed lunar granulite suite and how it records high temperature metamorphism within the lunar crust. So there we go. So yes, so the granulite metamorphism, it's the result of high temperature, and when we say high temperature, I mean peak metamorphic temperatures are around about 1,000 degrees Celsius. That causes recrystallization of hyaline lithologies. Now, the granulites, they're not a particularly dominant lithology in the Apollo collection. They're mostly present as small fragments and clasts within breccias and soils. They're most dominantly found out of all the Apollo sample collections from 16 and 17, where a few larger hand sort of sized, if you will, specimens were collected, such as the one that's shown on the right hand side there. But so really, I guess all of these, this sort of suite begs the question really, you know, how does high temperature metamorphism like this take place within the lunar crust? What are the sort of mechanisms that allow this to take place? And these are important questions to ask, as these give important insights into how the lunar crust and how specifically the primary and secondary lithologies within the lunar crust are modified over geological time. So I'm just going to spend 2 slides quickly just talking a bit about what I mean when I say a granulite, as this term is slightly different to how it's used in terrestrial metamorphic geology. In terrestrial terms, there's a very specific temperature and pressure connotation, whereas these are solely the result of high temperature, not pressure. And so in this regard, they're a bit more similar to hornfells for those who are more familiar with terrestrial metamorphic petrology. And so these have a wide variety of different textures that we see in the sample collection, and these are just a couple of examples, representative examples of some of the textures that we observe. On the right hand side, we see some sort of very nice granoblastic type textures, which is sort of classic recrystallization, where you've got plagies and olivines and pyroxenes intersecting at roughly 120 degree angles. Interestingly, there's also some poikilotic type textures, which particularly when they're sort of, these textures are found as small class, they can be quite difficult to identify these as belonging to the granulite suite, as opposed to, say, poikilotic impact melts. But more often than not, we see quite a lot of heterogeneity on thin section scales in terms of textures. You quite often see sort of more granoblastic type matrix with pockets of poikilotic type textures, showing that temperatures must have been elevated enough to result in very localized partial melting in some cases. And as I alluded to just now, these are the result of the metamorphosis of hyaline lithologies, and the chemistries show that the more ferroin examples are very similar to ferro and northosites. And this can be seen in the old classic plot of magnesium number and mafic minerals versus AN content in plagioclase. And the blue symbols here are the more ferroan examples from the granulite suite, and they fall very nicely in the fan field. The red samples are the more magnesium-rich subtypes, and these are a lot more similar in their composition to secondary plutonic rocks. They're not necessarily directly related to the MG suite. There's some subtle trace element differences that's represented on the right-hand plot here that mean they may not be directly related to the MG suite. The details of which are not too important for the purpose of this talk. The main take-home message really here is that the protoliths are a wide selection of both primary and secondary crustal lithologies. And the other important thing to note here as well is that they have elevated sidrophile element abundances relative to their pristine counterparts, suggesting that the protoliths are somehow been in the mix with some kind of impact event. So a lot of people have suggested that the direct protoliths, rather than pristine rocks, are somehow impact modified versions of these pristine lithologies. And so this loops us back round then to where in the crust is this high temperature metamorphism taking place, and what can we do to try and constrain some of these mechanisms that allow these granulites to form? And there are two sort of main hypotheses that have been put forward. The favorite and the one that seems the most airtime within the literature is that this high temperature metamorphism can take place around craters that are large enough to host impact melt sheets. And so the idea being, if you can imagine a nice thick and hot impact melt sheet, should have in principle the thermal conditions to heat the surrounding rock, either the megaregolith or on the crater walls, or some kind of megaregolith or fractured or brecciated material, or whatever material is sat below the impact melt sheet. I think it's important to also highlight that we can't discount the role that plutonic intrusions and basaltic sills and dikes may play in creating the sort of conditions necessary for granulite metamorphism. These are also hot bodies being intruded into the crust that may have the correct thermal properties to result in contact metamorphism around the edges. The one argument, however, that makes this slightly less likely is that these, in order to sort of preserve the elevated sidrophile element compositions, these would have to be, these can't be too deep in the megaregolith when the MG suite or whatever secondary plutonics are being intruded into the crust. They can't be, but anyway, I'll gloss over that as I see the time is ticking down. So how can we approach this then for constraining the impact melt sheet thermal conditions? And so I'm going to basically look at titanium in orthopyroxene. If you can imagine a pyroxene, minor and trace element zoning can help constrain the impact melt sheet thickness by looking at how fast minerals diffuse at a high temperature. And this is because if you understand how fast a major and trace elements move throughout, diffuse throughout a mineral, then you can effectively use that speed of diffusion to estimate how long a mineral's been held at temperature. And what we see is a range of equilibration ages for these samples. We see a range of zonation patterns. Some suggest that some of these profiles show very little zoning, others show quite some nice diffuse zoning patterns. And ages effectively date the metamorphic duration from hundreds of years to tens of thousands of years. And we can do a bit of thermal modeling to then try and constrain what thickness of melt sheet we need to produce this sort of length of period of metamorphism. And so this is just a plot showing temperature versus depth we did some very simple heat flow modeling using the classic equation of Jaeger from the late 60s. So this modeling basically shows on this plot of temperature versus depth, 0 being the contact between the melt sheet and underlying rock. I can go into the details of this modeling a bit more in the discussion later on, as I can see I'm nearly out of time. I've only got a few more slides to go. But basically, this model also takes into account the fact that the melt sheet will cool over time. And so what the thermal modeling suggests is that after, say, 300 years, the top, sort of the bottom 100 meters of rock will be the appropriate kind of temperature for granulite metamorphism. And then when you consider the closure temperatures of titanium in pyroxenes, oh, this is actually the wrong slide. That figure is incorrect. I do apologize. I must have loaded an old version of the talk. This should actually read 4 kiloyears. This should actually read 2, and this should actually read 150. So I do apologize. But anyway, the point being that after about, the thermal modeling suggests that after 4,000 years, a 700 meter thick melt sheet will be able to produce temperatures that will allow titanium to diffuse in the pyroxenes for 4 kiloyears. So that's consistent. And we can use the melt sheet thicknesses and this type of thermal modeling to estimate crater diameter. And just in the interest of time, I'll just leave these general conclusions is that granulites have the potential to form in a very wide range of impact locations. Our titanium zonings that we observed in these granulites suggest that craters, that you can get granulite metamorphism in craters that range from 60 kilometers in diameter above, which is actually the majority of craters on the moon. And so actually granulite metamorphism, despite the fact that not being particularly common in the Apollo collection, it should be a very important lithology associated with impact structures on the moon. So apologies for running over slightly, and I'll leave that there.
Thank you very much, John. 30 seconds if there's a question. Otherwise, we can put them in the chat. I have a question, but I'll just put it in the chat for you during the next talk.
Cool.
So let's move on to the next speaker. See, the next speaker is Shyama Narendranath, and she'll be talking about remote sensing minor elements on the lunar surface.
Yeah. Thank you. Hello, everyone. I hope my slides are visible.
You are in, you're not in presenter mode yet. We're seeing the slides on the, we're seeing the order of slides on the left there.
Okay, shall I go ahead?
If you go to slideshow.
Yeah.
There you go. Okay, you're good to go.
That's good.
You can start.
Yeah, hello everyone. So I'm Shyama. I'm at the Indian Space Research Organization. So we're going to talk about remote sensing of minor elements using the X-ray spectrometer on Chandrayaan-2. So class, very quickly, a brief overview is an X-ray fluorescence experiment, which covers the energy range from 0.5 to 20 keV. It covers all the major elements, which is what constitutes about 99% of the composition of the lunar surface. It also covers the range of elements from sodium to about manganese, which all are expected at very low levels. I say this because apart from these major elements, we are also detecting some of these minor elements, which I'll come to in the subsequent slides. Class has a footprint of 12.5 into 12.5 kilometer on the lunar surface. It's non-imaging, so at 100 kilometer altitude, this is the pixel that we see at any instant. The operation is continuous only on the sunlit side, and the X-ray fluorescent signals come only when we have solar activity. We also operate it every orbit for 5 minutes during the night side to get a background, so that we can do a good background subtraction. The coverage that we have until about this map is for about end of April 2021. It's color coded to show that there are regions where we have high spatial resolution. So the difference arises because the solar activity changes. So when we have very strong flares, we get the best spatial resolution, which is the orange to red regions. At other times, it's coarser. And when we say coverage, that means we actually see X-ray fluorescence lines of oxygen, magnesium, aluminum, and silicon. So that's the basis for the map. And as you can see, almost 95% of the moon is covered. And at particularly these red areas, we have up to iron mapping. And we do a spectral modeling, which takes into account the solar spectrum. because there is a solar monitor which simultaneously takes a solar spectrum. We have an instrument response modeled with ground and onboard calibration. Just also wanted to add that this is actually a continuation of experiments that were flown earlier on Smart 1 and Chandrayaan 1, which were European instruments. And uses the same detectors. So there is a very good model of the behavior of the detector is all understood from its flight heritage in the previous experiments. So we take into account all these and build a physical model of the expected X-ray fluorescence spectrum. So on the right is shown such a model. The green line is the model and the blue the data itself. So we take into account the X-ray fluorescence line flux for a given solar spectrum, as well as the scattered component, which is the continuum that's shown here, and as well as the geometry of the observation. But we do have uncertainties in some cases when the XSM does not see the sun. So there are many cases, unfortunately, in the orbit when the sun is not in the field of view of the solar monitor. And in those cases, we use the Gauss X-ray broadband channels to calculate the solar spectrum for the given temperature. But as you can see on the right, in those cases when we don't have XSM, particularly for higher atomic number elements like titanium and iron, the fits are worse than when you have an XSM solar spectrum. Below 800 eV, the response of the instrument is also not very well modeled. So though we see the oxygen line here, currently we are not able to model that very well. So working on it, but just to highlight the point that although all the major elements are covered, the highest confidence we have currently on these maps are for magnesium, aluminum, silicon, and calcium. And when there is XSM for titanium and iron as well, the oxygen abundance we fix in all these models. And for the other minor elements, which I'm going to come in the next few slides, the current uncertainty in abundance is 20 to 30% of that value, because we're talking about really low abundances. So the chromium and manganese are so far only measured in the Apollo return samples or meteorites, or basically in lab-based measurements. But here we see actually clear detection of chromium and manganese. These are two cases. One is Mare Nectaris, a track in the Mare Nectaris. And this is a very recent one where there was a very strong X-flare from the sun after about 4 years. And so here again, this pixel is on the far side, and you can see the lines from chromium and manganese. So basically what we observe is that in cases of very strong flares, we do see these lines of chromium and manganese. And there are really no solar lines in this energy range. There are no instrumental lines. And these line fluxes vary just like the other XRF line fluxes. So basically to point out the fact that this is indeed from the moon. So we have done that verification certainly. Also we see variations from pixel to pixel. Basically using this data, we're able to map the line flux or the signal strength difference in such minor elements like chromium and manganese.
4 minutes.
Yeah, so we did estimate the abundances from these using the model that I have discussed in the earlier slide, and this is the preliminary results shown here for a few cases. The chromium comes around 0.2 to 0.3%, whereas manganese we see a finer, much more variation between the pixels. This is for the case of Mare Nectaris. We also see sodium, which is again generally considered to be a minor element. But the detection is better during weak solar flares. So here you have the sodium line here, it's weak. And it is clearly discernible more for weaker flares because of the lower scattered solar flux, which increases the line to continuum ratio. In the case of sodium, there is much more wide detection because this happens even for weak solar activity. And the abundance estimates, there is a range which we are working on, but most of it is below 1 weight percentage. So in conclusion, class on Chandrayaan-2 enables detection of minor elements, which is for the first time through remote sensing. Currently, we're mapping chromium and manganese during strong solar flares and sodium during the weak solar flares. So that's all I have. Thank you.
Thank you very much. Any questions for Shyama? Checking the chat. Can you comment a little bit more detail on the frequency of the solar flares and how often they occur to allow you to see chromium, manganese, and sodium? And are we in a position where the sun is the sun's activity is increasing or decreasing, so you should expect to see more or less?
Right. So 2019 was the very solar minimum, much more than the previous years. So the activity has been very low, but recently it's picked up, and we had 2 M flares and the next flare in the 3rd of July, which shows that sun is on the ascending phase. So we expect more signals.
Wonderful. There's also a question here from Mahesh Anand. For the track for the far side where you saw the increased chromium manganese, was that for a Mare patch?
No, it wasn't. So I don't know the connection yet. So probably we do have to have a map to really connect to the source. So that was a highlight.
Cool. Don't see any additional questions right now, but if there are any additional questions, we can see them in the chat. So thank you very much.
Yeah, thank you.
The next talk is by Christopher Kramer, remote magnesium number determination of olivine and pyroxene in the 4 to 8 micron crossover range. We can see your slides and we can hear you.
Okay, great. So everything looks good for you guys?
You're good to go.
Okay, so thanks for that introduction, Tim, and thank you all for being here. Today I'm going to present the results of my PhD dissertation in progress. Today I'm going to be talking about a novel infrared spectroscopic technique called crossover spectroscopy and its application to the remote determination of olivine and pyroxene composition. Visible near infrared and mid-infrared remote sensing have been crucial to revealing the distribution of minerals on the surfaces of planetary bodies. But constraining the compositions of solid solution minerals, such as olivine and pyroxene, has remained difficult for these techniques. And this leaves many unknowns about the crustal evolution of solar system bodies, including the moon. To put it in graphical terms, we're able to identify the presence of minerals such as olivine and pyroxene, but we're not sure what kinds of olivine and pyroxene or where in solid solution space we think these minerals reside. So in 2020, my collaborators and I published a paper using this technique called crossover spectroscopy to determine Mg number of olivine. So what is the crossover range? The crossover range, which I'll also refer to as the 4 to 8 micron wavelength range, is a range of the infrared where silicate bands arise as overtones and combinations of the fundamental vibrations which occur out in the mid-infrared wavelength ranges. In this wavelength range, bands tend to be stronger for samples with smaller particle sizes, and our group has ongoing work on the influence of space weathering on spectra in this range, on the systematics of mineral mixtures, and the interaction of silicate and H2O bands in this range. So on the left-hand side, we see a plot of reflectance spectra of synthetic olivine with more Mg-rich samples on the top and more iron-rich samples on the bottom. And the dashed lines highlight strong spectral bands at 5.6 and 6 microns. these bands shift systematically to lower, to longer wavelengths or lower wave numbers with increasing iron content. And we assembled a large data set of olivine samples that were synthetic in origin and natural in origin. And among the natural samples that had terrestrial and extraterrestrial origins, including 2 Apollo samples. And what we saw in these 2 data sets is summarized here with the trends in the band minimum position for the 5.6 and 6 micron bands shown on the left-hand side and the right-hand side for the whole data sets. We see strong consistencies in these trends for the samples of various origins and for reflectance as well as emissivity spectra. And so the upshot of all this is that in control laboratory conditions, we can determine the mg number of olivine within plus or minus 5 mole percent using band position alone. So this was a very exciting result. And what we wanted to then ask is, what about pyroxene? As you can just tell graphically, pyroxene is a more complex solid solution. So using visible near-infrared spectroscopy, we are able to distinguish between high calcium pyroxene and low calcium pyroxene, or clinopyroxene and orthopyroxene. And this work goes back to a number of foundational papers, including work by Rachel Klima and others. Now, while that holds for V-near spectroscopy, telling apart magnesium-rich and iron-rich pyroxenes without a priori knowledge of the calcium composition of pyroxene has proven challenging. And so this seemed like an interesting task for infrared spectra in the 4 to 8 micron range. So what we have done is we've assembled a set of spectra measured over many years by numerous investigators of synthetic and natural samples. Now, these samples are generally pure and well-behaved as far as pyroxenes go. They show relatively low degrees of zoning, but some of these do show cationic impurities in X-solution lamellae. Included in this data set are diogenites and enstatite chondrites, which are relatively well-behaved. And we have ongoing work on some of the naughtier pyroxenes, if you will, from such samples as lunar basalts. So in any event, these are the samples we've looked at. And I want to show you some of these spectra, step you through them step by step. So on the left-hand side, we see a plot of reflectance spectra of low calcium pyroxene or orthopyroxenes. And the band that's the most important here is this strong spectral band at approximately 5.1 microns. Now, at the top, we see high Mg samples. At the bottom, we see low Mg samples. And we can see that this spectral band shifts systematically in its position with a decrease in iron composition. Now, in the clinopyroxene samples, we see spectral bands at about 5.05 microns and 5.3 microns. And these spectral bands exhibit the same behavior. Now, we looked at a whole lot of spectra, and I'm going to spare you looking at all the spectra and just show you the results of our work so far. So on this plot, we see a summary of the relationship between band position and band minimum position and Mg number. And so going from left to right, we have the 5 micron band, the 5.1 micron band, and the 5.3 micron band. And for these relatively pure pyroxenes, we are able to use laboratory spectra to determine Mg number within plus or minus 7 to 10 mole percent, which is in agreement with the relationships found by Hamilton for the mid-infrared range. So looking at both the olivines and pyroxenes, we see that crossover spectroscopy has strong promise for determining the Mg number of 2 of the most common mafic minerals. So now, if we want to think about how we're going to apply this to real rocks, we need to think about systematics of mixtures, and we need to think about space weathering. And so Ben will talk about this at much greater length in his own talk right after this one. But when we look at mixtures of anorthite and forsterite, what we see is that the olivine bands remain strong and do not shift in their position, even to relatively low weight percent, which is very promising for the remote sensing of lunar troglodytes. And then finally, in our collaboration with Jeff Gillis Davis, what we have found is that experimentally produced nanophase iron shows only a modest effect on the position and strength of the olivine bands in the 4 to 8 micron range. So in any event, I'd like to thank you all for your attention, and I'd like to thank my collaborators and data sources. And as I'm looking for a new job circa May 2022, if you have any interest in working on this new technique with me, I'd be more than happy to hear from you and to talk more. So thank you very much.
Great talk. Thank you, Chris. I think Katie's question is not for you, not sure. But can I send you some synthetic pigeonites to measure?
Please.
All right. Consider them in the mail. Yeah, her question was for the last speaker.
Yeah, okay, I wasn't doing it with oxygen fugacity, so. Okay, cool. Well, I'll stop my share.
Great. Thank you very much, Chris. So the next speaker, if there's any other questions, please put them in the chat for Chris. And so the next speaker is Benjamin Greenhagen, who's going to talk about unmixing lunar surface compositions using near-infrared and thermal infrared data sets, connecting orbital and laboratory measurements. So you're good to go, Ben.
Great. Thanks, Tim. Can you hear me?
Yes.
All right. Yeah, and thanks for the shout out in the previous talk as well. I will talk about those samples in just a little bit. Okay, so yeah, so this work, we're going to talk more about near infrared and thermal infrared, but we're going to step back just a little bit to what we can see from orbit and what we can do in the laboratory to understand those orbital data sets. So Chris just gave a really nice description of all of the variations inside the pyroxene and olivine compositions. For this talk, we're going to assume that those don't exist, at least for right now. And we're going to talk about ternaries of plagioclase, pyroxene, and olivine. And so these are two summary plots from earlier work, Lucy 2006 on the left and Cahill 2009 on the right, showing where lunar soils on the left in these blue shades fall on this three-component ternary through measurements of return to Apollo soils. And then on the right, the different gray shades are rock lithic fragments within return to Apollo soils, showing that the soils themselves, these ground up material, does not show the same compositional range that the lithic rock fragments do. And then also on the plot on the right are some red diamonds that show central peak compositions determined from near-infrared spectroscopy. And one of the things we want to work on in this work is how we can get better constraints on composition by including thermal infrared, which has different dependencies on composition. So in the thermal infrared, we have typically, for the moon, I should say, we've been using the Chris-Johnson feature as our indicator of silicate mineralogy. The plot on the lower right shows for different compositions what emissivity spectrum in a simulated lunar environment look like. And this broad peak is the Chris-Johnson feature. It shifts to shorter wavelengths for things like plagioclase and longer wavelengths for more mafic things like olivines. The highest sensitivity that we have with this value is the plagioclase mafic abundance. So if you look at this ternary in the upper right-hand corner, I've now basically colored it to an approximation of what the CF would be doing across this space. And you can see you get the greatest color difference on that plagioclase to olivine line, the troglodyte line, than you do in the other spaces. And we want to use this phenomenon that we see in thermal infrared spectroscopy, along with the really great constraints on mafic compositions you can get from near infrared spectroscopy. So getting very detailed information about what the pyroxene to olivine ratios are specifically. So if you imagine having two compositional potential lines, these plots in the bottom right hand are showing what you get from the thermal infrared in the solid line and the near infrared in the dashed line, and you can get a very tight constraint. So that's the thesis behind this technique, and it's something that we've been working on for a number of years, and it's been funded by LDAP to do this work. Oh, and I should say before I go on here, for this study, we're using Diviner and multiband imager data. Those are the two data sets we're using, but this can apply generally. So moving forward, if you have a great mission like Lunar Trailblazer that can get both that near infrared spectra and the thermal infrared spectra at the same time, you could solve this simultaneously with coincident measured data, and that would be absolutely fantastic. Okay, so really what we're trying to do here is go from this plot in the upper left-hand corner, which is the Christiansen feature values measured by Diviner, to this plot in the lower right-hand, which is the modeled plagioclase abundance. And to do this, Paul Lucy came up with this algorithm. And you can see the flow chart on the right. This is pretty complicated, but there's just a few basic steps. The first one is to take our Christiansen feature values and correct for space weathering effects. That's the top part here. After we do that, we use a series of equations to combine the Kaguya multiband imager existing mineral abundances and the laboratory end member values to produce a new plagioclase abundance map that I just showed. This is then iterated with Lunar Prospector GRS to validate it and stretch it so that the units are accurate. And then we bring that back in to a second iteration with the mafic abundances to get what the final olivine and pyroxene abundances are. So if you're interested in taking a deep dive into this, that there's a link to the paper here. If you just Google Lucy Diviner 2021, the first thing that shows up is this paper. And inside it, there's also links to these data products. So our CF map I just showed is on Zenado there. All of these green box products are also there. So please check it out. And it is just more than mineral maps that we've been doing with this. In particular, we did a significant improvement of the space weathering correction. Originally was published back in 2017. There's now a new version that takes into account iron abundance as well. And a discovery, I should say, of this work was that if you do a decorrelation between Christiansen feature value and FEO, you get really some of the most interesting spots on the moon come out as either dark or bright anomalies. So dark anomalies have a iron deficiency, and they include the plagioclase and silicic anomalies. And bright anomalies would have an iron excess, and they include areas like the olivine-rich areas around Moscoviense, and also, interestingly, lunar swirls. This data product is also available there too. Thanks, Tim.
4 minutes, Ben.
Got it. So flipping over to the other side, the lab measurements. So this is what Chris just mentioned. We have 49 mixtures that we created across this ternary to do the laboratory measurements on. We used Miyakijima anorthite, which is the most lunar-like anorthite. And then we used a forsterite and Tanzanian enstatite. And we are focused just on the finest size fraction for this work. And all the measurements were made in our simulated lunar environment chamber at APO. This is a work I described last year, so I'm going to go through this pretty quickly. This is what our updated ternary looks like if we assume our updated M member values, similar to what has been shown before and published previously. If you include all 49 mixtures across the ternary, you get something that looks pretty different. But the good news is that if you go across this ternary in different directions, they're actually very smooth trends, nearly linear trends, except for when you get to the very high olivine abundances. And so that's something we wanted to look at a little bit more. And in particular, because of the method we used a constant lamp temperature. And so the samples we're measuring, which we're measuring in thermal emission, were actually physically different temperatures for these measurements. So we wanted to make sure that that wasn't a factor. After we took 2 years to measure 49 spectra, we measured 49 more in considerably less amount of time. And we got essentially the same answer. So this nonlinearity that's associated with the plagioclase to olivine, the troctolite line, is not a temperature effect. So that is good to know. And then I should say that this is actually inconsistent with some results we did on Apollo soils by varying temperature. So something is going on between these pure minerals and more real geologic space weathered samples that will be a future investigation. So in summary, how we can take this back, to the mineral map data is that in both cases, we have linear trends. So we will be able to update the algorithm, but honestly, we expect fairly minimal differences because of the work that we already did tying things to the Lunar Prospector GRS and to the near infrared. But if there are differences, the area they are going to occur is in that troctolite corner. And with that, I will stop.
Thanks a lot, Ben. Questions for Ben? Chat. We'll say that's a very nice flow chart.
It is. I'll go through a link to the data locations into chat too, so people can go right to them. They're open access, so you don't have to have any subscriptions to get them.
Question from Mahesh: are agglutinates messing things up in the Apollo samples?
Yeah, it's probably something related to the agglutinates or the fact that the Apollo samples actually have quite a wider range of particle sizes than what we were looking at. We really only included the finest grain, whereas the Apollo samples we measured had the full size distribution up to, I think, 200 microns in them. And so those can create little thermal shortcuts on these types of textures we're looking at. So agglutinates, opaques, different grain sizes, all of those are going to be complicating factors.
Imagine all the visible albedos of all of your samples were probably much brighter than the Apollo samples.
They are.
Sorry.
Yep.
Right, we're out of time on this talk, so any further questions can go in the chat, and I will turn it over to my distinguished co-chair, John.
Cool, thank you very much. Okie dokie. So next up, we have Chiara Ferrari Wong. If you are here, feel free to, excellent, fantastic. So I will set the timer. We can see your slides okay.
Okay, great.
And I will start the timer whenever you're ready.
All right. Well, hello. Today I will be presenting Lunar High Tide, which is a thermal infrared hyperspectral imager concept for meter scale data collection from orbit. Lunar High Tide is a hyperspectral mapper that uses thermal infrared spectroscopy to detect silicate mineralogy, as well as the 6 micron emission feature to detect molecular water. It does so at 4 meter scale spatial resolution, which is 4 times that of any previous or planned orbital spectral remote sensing experiment. I'm going to start with this slide emphasizing the key takeaways of what I'll be talking about today and what Lunar High Tide would be able to achieve. In the science realm, Lunar High Tide would enable direct hyperspectral measurements of mineral compositions of individual lunar boulders, as well as characterize the mineralogy and water content of the deposits of small fresh craters with diameters as small as 10 meters. This capability would also work hand in hand with Artemis mission support, as it would be able to map the lunar South Pole and provide mineral compositions of every small crater and large boulder in the polar regions. So Lunar High Tide addresses 2 major scientific questions for the moon directly from the Planetary Science Decadal Survey. The first of which is, how do the structure and composition of each planetary body vary with respect to location, depth, and time? And the second is understanding the composition and distribution of volatile chemical compounds. And so in addressing these questions, Lunar High Tide will provide maps of the mineral compositions of small fresh craters and boulders, as well as map the distribution of molecular water, like I said before, globally and at Artemis sites. So we'll dive a little bit deeper into some of the science measurements here. The first of which is hyperspectrally measuring mineral compositions of individual boulders and small fresh craters. The reason why we would want to look at boulders is because rocks exhibit less mixing than soils and are less space weathered than soils, since their lifetime on the surface is limited by impact and thermal breakdown. And while many highland rocks are mixtures themselves or breccias, If we were to look in settings like basin rings and central peaks, we might be able to find boulders of primary igneous lithologies. And with lunar high tide, we would be able to collect this data at 4-meter scale spatial resolution, which would thus increase the likelihood of finding a boulder of primary igneous lithology. In terms of these measurements and Artemis's science goals, high tide will work on determining the extent and composition of the primary feldspathic crust through measuring the feldspar to mafic ratio of anorthosites, determining the inventory relationship and ages of non-Mare rocks through determining lithologies present at the central peaks and at silicic volcanic constructs, and then also work towards the goal of determining the bulk composition of the mantle by seeking evidence of ultramafic rocks in basin rings and pyroclastic deposits. Our second major measurement would be to map the distribution of molecular water globally and at Artemis sites using that 6-micron emission feature, which is the same emission feature that Honeyball et al. 2021 detected using an airborne observatory. And this would be to understand the composition and distribution of volatile chemical compounds on the moon. So some additional goals and Artemis for Artemis support are that along with mapping the 6-micron feature, lunar high tide would also be able to detect changes in the molecular water signature due to spacecraft traffic and surface operations. It would also be able to determine silicate mineralogy and water content of boulders and deposits of small craters, specifically to inform pre-mission EVA planning. It could search for exotic material deposited maybe from the rays of Jackson and Tycho. And then additionally, it could map the distribution of micro cold traps within 10 degrees of the pole by measuring the temperature at high temporal and high spatial resolution, which would be 4-meter spatial resolution. Lunar high tide itself, as a concept, is a maturation of high tide, which is also known as the hyperspectral thermal imager. It's currently being constructed under NASA's Earth Science Technology Office's INVEST program as a 6U CubeSat mission that's scheduled to fly in early 2022. High tide as it currently exists does not meet lunar science requirements because it has a low frame rate detector system. It's been designed for low vibration launch and as well as been designed for low Earth orbit. So in terms of a lunar application, high tide's technology readiness level is a 4. But now lunar high tide is nearly identical to high tide, but there are a few exceptions. So the first of which is that while lunar high tide is going to use the same infrared detector array as high tide, it will use a high-speed readout integrated circuit, or ROIC, in order to meet spatial sampling requirements. It will also have radiation-tolerant camera electronics. It will have to be ruggedized and tested to the general environmental verification standard for planetary launches. This thermal design will be upgraded for lunar orbit operation, and then it will use an athermal telescope, while terrestrial high tide uses a focus mechanism on the telescope objective. Now, lunar high tide is going to operate between 5.5 and 11.5 microns at 10.8 wave number resolution to map water, silicates, and other mineral emissions. From a 20-kilometer orbit, the diffraction limited spatial resolution is going to be 4 meters, and the swath width is going to be 1.4 kilometers. The signal to noise ratios vary from about 150 near 6 microns to over 1,000 past 9 microns for surface temperatures between 250 Kelvin and 300 Kelvin. And these signal to noise ratios meet or exceed the TESS and THEMIS signal to noise ratios that demonstrated successful mapping of silicate minerals on Mars using their features in the 7 to 14 micron region. Broadband thermal imaging using the instrument is also available and at 4-meter resolution, and the noise equivalent delta temperature is 1 Kelvin at a surface temperature of 50 Kelvin and about 1 millikelvin at a surface temperature of 300 Kelvin, which is sufficient to characterize any nighttime surface outside the PSRs. So I'm going to expand just briefly on the instrument spatial resolution. Lunar high tide is able to achieve 4-meter spatial resolution with its current optical design. However, there is enough signal to achieve our science goals at 1-meter spatial resolution, but it would require a very large telescope. And also an optical, and thus it would require an optical redesign. Regardless, the data products that Lunar High Tide would return would complement Lunar Trailblazer's wide field of view with very high resolution composition and temperature measurements in the thermal infrared. So finally, we wanted to conduct a general survey from the population here. I know everybody here really likes acronyms, but we were thinking about renaming this concept Rockstar instead of Lunar High Tide. So if you'd like to leave a comment in the chat saying which one you prefer, and if you hate acronyms, you might hate Rockstar. We never know. Or yeah, okay. Anyway, so here's the summary once more. In some new developments for this concept, we recently submitted a DALI proposal to conduct advanced development of this instrument for future lunar missions, and we plan to propose to the next Simplex call. Anyway, thank you very much. I can be reached for questions at that email or in the chat or in the question section. So thank you very much.
Brilliant, thanks very much. Maybe we could get a poll up together on Zoom during the discussion section, if you like.
That'd be great.
So yes, once again, please do write any questions in chat. And while people are typing, I guess I've just got a quick question really. When you sort of talk about wanting to map boulders and stuff, do you expect these boulders, sorry?
Oh, sorry.
Sorry, do you expect that the boulders to have quite fresh surfaces, or are they expected to have lots of sort of dust covering from nearby sort of cratering impacts and stuff like that? Do we know that, or is that a big unknown?
I think I'm not quite sure. I would expect them to be relatively fresh because they are less weathered and than say like soil. But yeah, I'm not actually 100% sure on the dust cover.
There's a lot of support for Rockstar in the chat, it seems. Okie doke. Well, yeah, if there are no other questions, I guess we'll thank Chiara once again and move on to the next talk.
Thank you.
So next up, we have Yang Gao, who is going to talk a bit about a phase study on lunar volatile and mineralogy mapping orbiter mission. Yang, if you're there.
Yeah, I'm here. Can you see my screen?
Yep, we can see your screen, and whenever you're ready, I will start the timer.
Thank you, John. Hello, everyone. It's a pleasure to be here speaking on behalf of the VMMO consortium, consisting of members from the UK, Canada, Portugal, and the Phase A study for the mission is managed by European Space Agency, the CubeSat office at Aztec in Netherlands. Just some quick words about the history of the mission. The concept has started since early 2017 in response to ESA ITT on 6 Nova Challenge on Lunar CubeSat for Exploration program. And we've been very fortunate to be selected as one of the joint winners for the challenge. And that gave us the opportunity to use ESA's CDF facility to further the study in mid-2018. At the beginning of 2020, the formal Phase A study sponsored by ESA was kicked off with a consortium that you are seeing today. And we have successfully completed the Phase A in March 2021. In this Phase A study, there are a number of flight opportunities we have assumed for orbital release of the CubeSat that include 2 NASA programs, the Whipper and Artemis 2. Just to highlight objectives of the mission, there are 2 folds. Technologically, we're looking at demonstrating beyond LEO, 12U CubeSat, its feasibility in terms of using some of the COS electronics as a test bed and semi-autonomous operation, particularly in terms of navigation and ranging, considering another potential onboarding SS receiver. There's also a tech demonstrator on
optical high-speed direct-to-earth downlink. This is likely to reach up to 100 megabps. Scientifically, we are looking at mapping, principally volatile mineralogy, using multi-wavelength LiDAR. There are multiple channels for the payload, and looking at abundance mapping for water ice and ammonite in this case. In terms of the target area, we are looking at South Pole Shackleton crater as a priority for the mapping for the science payload, and it's not very difficult through the STK simulation to establish how long the mission has to be in order to map a crater as a size of 20 kilometers across the diameter. So giving those information in hand, and we also had various mission constraints provided by European Space Agency during the phase A. Everything had to be accommodated within a 12U CubeSat with a bed mass up to 24 kilo with margin. In terms of the CubeSat deployer, we are looking at ISIS COPPAD 12U XL. And as mentioned earlier, there are 2 NASA missions that have been baselined to potentially inject the CubeSat into a transfer orbit. Launch time frame, we're looking at Q4 2023 or up to 2024. 1 year mission duration as a baseline in order for us to cover very well the entire Shackleton crater. So this is a slide give you a kind of overview of mission profile, very much echo what I said earlier, from the integration with the mother spacecraft, depending on which flight opportunity we have in mind, up to launch and transit to the moon. Of course, the spacecraft release, that includes a detumbling, solar array deployment, and of course, the orbit acquisition, which, here we're assuming a lunar frozen orbit as the final orbit, and that lead to the start of the 12 months operation for the mission. I think it's worth highlighting some of the operational concept for the mission, particularly some of the communication routes, if you like. There are 3 communication routes back to Earth. There's UHF link via the SSTL Lunar Pathfinder orbiter. That's going to go through the Green ground station based in the UK. There is S-band, X-band, depending on whether we have the GNSS on board for ranging. Direct-to-Earth link, which rely on either UK-based or ESOC-based station network. Also, last but not least, the communication to support the optical data link, which has to be using an ESA station, which is equipped to support that. The spacecraft operation is going to be based at Surrey in the UK, and the payload operation is going to be managed by MPBC, our partner in Canada. Of course, the rest of the consortium is split into these 2 teams to support the platform operation and the payload. The science team is obviously going to be in charge of the processing, distribution, and archive of the scientific data and how to interface some of the data outputs with support from the international science community. A few words about the science payload requirements for phase A. There are 3 channels for the LiDAR to support active mode. where we want to achieve the signal to noise ratio for about 30. Ground sample distance within 10 meters. For the passive mode, we're looking at 4 channels to support mapping both the water ice and ammonite. So for the payload, it needs to be kept within the 5U of the platform and has to be less than 7 kilo, and the peak power has to be kept at 140 watt. This is just a overview of the configuration of the CubeSat from the outside. From the inside, there's a bit more information here about the data bus and the power bus. As you can see, we baselined the CAN bus principally, supported by space wire. And there's something we're also using RS422 to support the control of the electrical propulsion. This is a summary slide to just confirm that the phase A managed to keep everything within the mass budget we're being asked to do by ESA. So all the subsystem has been kept within 24 kilo with a reasonable system level margin of 15%. The breakdown of different subsystems in terms of percentages, quite reasonable. I would say if you look at the statistics, this is not far off from what typically happen in satellites in average. I just quickly ask John, do I have 4 more minutes?
It'll be 2 minutes once the clock reaches 4 o'clock.
I didn't realize I can go so fast, so I can go quickly to some of my spare slides, utilizing that 2 more minutes. So just a few backup slides to say a few more words about the payload itself. As you can see, it's broken into 2 operational modes. For the passive, it's looking at the reflectance ratio between the 4 channels we have there, 532, 1064, 1535 to 1560 nanometer, and there's also ultraviolet channel at 290, which provide additional safety guard for the data acquisition. Well, for the active mode, where we have less channels to look at in this case, 3 channels, and in terms of the data acquisition during passes, which are looking at both day and night, we will be looking at over at least 1 or more Apollo landing site. This is really to facilitate calibration, both offline and online. Just to present a few additional graphs here in terms of the actual working principle of the payload. And here we are looking at absolute reflectance and reflectance ratio. Of course, in terms of ratio, that gives us less ambiguous results in terms of mapping the water ice abundance. So here is a similar slides, but in this case, looking at the mineralogy, detection, mapping. As you can see, there's some data graph acquired from the lab work, which shows the principle does work because it gives quite distinctive gradients here in terms of the graph. And there's also the wavelength plot looking at the ammonite detection through its reflectance and how that is compared looking at the existing data points based on the highland soil and marl soil. I think I might hit my time budget, so I better shut up, but I can leave this slides here as ending slides, which kind of show you a comparison of the coverage of the Shackleton crater based against the different orbits we have analyzed during the phase A study. There is also extra information about how it looks like compared to Fustini, just in case we have interest there too. Hope that's okay.
Brilliant, thank you very much. So again, we'll take maybe just one quick question if anyone has one ready to go in chat. Otherwise, we're running a little bit behind schedule. So if there's nothing forthcoming in chat, we should probably move on to the lightning talk section. I'll just wait a few seconds in case there are any messages that filter through. Okay, yeah, so feel free to continue to asking questions, of course, in chat throughout. But yeah, we should probably move on then to catch up a little bit of time with the lightning talk section. And so next up, we're going to move on to these 2-minute flash talks. And so if the next talk then will be by Ryan Galinkin, if you're about and are ready to go.
Excellent, thank you.
Fantastic. I will just load up the 2-minute timer.
And you said my name correctly, so that was pretty good.
Cool.
All right.
Right, so we've got, you see your slide, and I will start the countdown whenever you're ready.
All right, I should be good now. So hi, everyone. My name is Ryan Galinkin. I'm a third-year graduate student at the University of Central Florida, and I work with my advisor, Dr. Carrie Donaldson-Hanna. Most of my research involves looking at thermal infrared spectra of the lunar surface. And I have a poster characterizing the effects of porosity and particle size on thermal infrared olivine spectral features. It's a mouthful, I know. That'll be tomorrow. And basically that's revolving around 2 separate goals here. The first one is, can you determine surface porosity from an image? That's always been difficult. A lot of studies use bulk porosity instead of surface porosity. And the other part of the study is, can you actually disentangle the effects of surface porosity from that particle size on our thermal infrared spectral features? If you find that interesting, or you just want to stop by, please feel free. I'm in, what do we got? Thursday, July 22nd, so that's tomorrow, 9:30 a.m. Pacific Standard Time, which is on my time, 12:30 p.m. Eastern Standard Time. Poster session 3 in surface composition and sample analysis, which I think most of the people here are interested in. And I'm poster number 8. So I hope to see you guys there. Thanks.
Brilliant, Ryan. Thank you very much.
Now, how do I stop the share for you guys? There we go.
There we go. Fantastic. Awesome. Cool.
Thanks, guys.
Okie doke. So next up is, let me just pull up the program here. So Krishnan Kumar Banot will be up next to give a flash talk on spinel symplectite textures in lunar dunites, a couple of lunar dunites from Apollo 17.
Can I just share my screen?
Yep. Okie doke. We can see your slides, and I will start the timer whenever you're ready.
Okay. Hello, everyone. My name is Krishnan Banot. I'm a PhD student at Birkbeck University of London and the Natural History Museum, London. My supervisors are Professor Hilary Downs, Chiara Patron, and Emma Humphrey-Williams. This study investigates spinel symplectites in lunar dunite samples collected by the Apollo 17 astronauts. Micro-CT imaging has established the 3-dimensional texture of the symplectites, which are integrals of spinel and other minerals. The host dunites are brecciated, and shock features indicate that they experience shock pressures in the order of 50 gigapascals. 4 types of spinel symplectites have been identified, varying in size, mineral associations, and spinel composition. Based on texture and mineral chemistry, we propose that the 4 symplectite types have different origins. Each represents a different stage in the history of the dunite. A common spinel type consists of ellipsoidal spinel pyroxene clusters, 0.3 millimeters in size, composed of integrals of vermicular spinel, CPX plus or minus OPX plus or minus Fe metal. This is the oldest texture and indicates the sample originated at depths of 420 kilometers, which is equivalent to 22 kilobar pressure in the lunar mantle. It represents the transformation of garnet to a spinel pyroxene cluster due to mantle overtime, which brought the dunite to pressures of 8 kilobar. 2 other samples of spinel symplectite have igneous textures resulting from interaction of basaltic melts with the shallow mantle prior to the Serenitatis impact. They are much smaller than the spinel pyroxene clusters, but can be imaged in 2D slices of CT scans. Another large symplectite type represents the youngest spinel texture and contains anorthite, indicating low pressure formation. It was most likely formed from the impact melts during the Serenitatis event, which excavated the sample from the lunar mantle to the surface. Thank you.
Brilliant, Christian. Thank you very much. Okie doke. So next up on our lightning talk, we have David Black. Is it going? And so you're going to give a lightning talk on 3D modeling of commercially viable lunar materials. So if you're able to share, oops.
Christian, can you stop? Yeah.
That's my screen, sorry. Okie doke. David?
Can you see our screen?
I can see part of a screen and a lot of your desktop. Oh yeah, that looks a bit better. Yeah, perfect, fantastic. And I'll just set the timer whenever you're ready.
Okay, we're ready to go. Well, as was said, my name is David Black, and I'm a high school science teacher at New Haven School in Spanish Fork, Utah. And our team has been part of a research project called XMASS, which is exploring the moon and asteroids with secondary students. I have with me 2 of my students who will help talk about our results here. Our mentor teacher through this program is Dr. Michelle Kirchhoff from the Southwest Research Institute. And our project is to look at how we can take 3D altitude data from the LOLA instrument on the lunar orbiting Lunar Reconnaissance Orbiter and turn it into 3D models and then map some mineralogical data on top of it. So some of the minerals that we looked at were mostly from the M3 instrument on Chandrayaan. And the minerals include helium-3, titanium, thorium, and others. And we're looking to see if we can determine whether these minerals might be commercially viable for lunar mining. So I'm going to turn this over to Paige Williams and also Julia Walsh to talk about our results.
Hi, I'm Julia. When we mapped photographs of the moon over our 3D model of Clavius crater, along with the path that the SOFIA telescope took, we can see that water ice discovered by the forecast instrument may originate from a ray blasted out of Tycho crater.
So when we were deciding on sites for in situ research on the moon, we would suggest the areas of Aristarchus crater and Schroeder's Valley. Not only does it suggest interesting lava tubes, contain interesting lava tubes and rills, but deposits of lunar anorthosite, the original bedrock of the moon, have been uncovered in Aristarchus, along with high levels of thorium. Retrieving samples would allow us to date the age of the moon in this region.
Titanium dioxide and helium-3 are found in the Old and Maria basins along the equator in Mare Tranquillitatis and the southern edge of Mare Serenitatis. Younger craters such as Theopolis are relatively low in helium-3. Looking at the probable costs of lunar mining and the local abundances of valuable minerals, we were able to conclude that lunar mining can be commercially viable.
As you can see from the images that we have here, we basically took maps that have already been created in the literature that we found, and then mapped it over the surface of our 3D models, and then used some Photoshop puppet distortion filters to get the data to match up. As you can see here in the picture of Aristarchus crater, the blue inside the crater represents lunar anorthosite, which would be very useful, as Julia said, for us to be able to see the age of the bedrock in this region. On the map on the right, the dark brown areas indicate high levels of titanium oxide. And
sorry to press you, we're slightly out of time. We should probably move on.
Okay, all right, sorry.
But that's quite all right. But yes, but your poster will be there tomorrow, won't it, during the session, if people want to find out a bit more.
Okay, yeah, sorry, I didn't realize we'd gotten that close. Thanks.
Okay. So finally, before we enter into our discussion phase, I'd like to welcome Amanda Stademan, who will give a flash talk about some preliminary petrological characterization of Apollo 16 class-rich impact melt rocks. And this will be our final flash talk before moving on to the discussion.
Hi, thank you. Can you hear me all right?
Yep.
And you can see my screen?
Yep, looks good. And that's all yours.
Great, thanks. I'm Amanda Stademan, a senior PhD candidate at the University of Arizona. In the sample science poster session tomorrow, I'll be presenting work on 2 Apollo 16 impact melt rocks, 64455, shown in the image on the right here, in optical light and elemental X-ray composite, and 68815 at poster number 10. These rocks contain glassy impact melt and embedded lithic and mineral fragments. We are looking at these rocks to investigate how contact metamorphism affects endogenous lunar material, geochemically, petrologically, and structurally. To date, we have observed that some minerals preferentially decompose in contact with impact melt, and also identified some pleonastic spinel-bearing clasts in 68815. From the data we collect using primarily electron microscopy, we will build a model for how impact melt contact metamorphism operates on the moon. Thanks.
Fantastic, thank you very much. So I do believe that concludes all the talks from this session. So thank you once again to everyone who's spoken this evening or this afternoon. So yes, I'll give a virtual round of applause to all our speakers. And yes, I guess now we have some discussion time allotted.
If there are any additional questions we want to put in the chat, we can put them to the speakers. And this can include both the 10-minute speakers as well as the lightning round presentations. Maybe I'll ask a question to David Black and his students. There's a nice presentation. I'm looking forward to seeing the full poster tomorrow. Do you view this project as, is this project kind of going on over multiple semesters or multiple school years? Do you have a plan for where this goes next?
XMAS program is just for the year before we present here. So it's just been the 2020-2021 school year. So of course, there's lots of ways we could continue this. This first project was mostly to kind of get used to working with lunar data, to work with the 3D altitude data, learn how to use that, how to map minerals on the surface. But the next step would be learning for ourselves how to use the M3 data, which that's a tall order, learning how to work with all the spectrums and so on that come from that. But one step at a time. The students that I have are going to be leaving pretty soon, and so I have to start up with another group of students pretty soon if we're going to continue this.
Great. Thank you very much. Don't be shy, folks. Everybody agrees Aristarchus is an awesome place on the moon. So good choice there.
Hi, I have a question for Chris Kramer. Is he still here?
I'm still here.
Hi, Chris. What was the result of your olivine magnesium number determination on the surface of the moon? You talked a lot about how you did it, but
I
there
see
was
what you're
no number
Oh,
that
right.
came out of it.
That's because the instrument doesn't exist yet. And I think that's where Kiara Ferrari Wong's presentation comes in. So sorry, I didn't, I should have made that more explicit. Such measurements, to my knowledge, have yet to be made. And this is all lab validation for when it will eventually be made.
Okay, but you had some lunar rocks there, so you were just using lunar olivines to.
Those were Apollo samples, correct? Yeah.
Okay. Thank you. That wasn't clear.
Yeah, really important point. Thank you for raising that.
And there's a related question from Paul Lucy in the chat, Chris. Have you measured the features in thermal emission or only in reflectance?
Yeah, I have. So I have. I showed reflectance spectra only for the sake of brevity, but for many samples, I have emissivity measurements. I have and many of these have been provided by collaborators and various colleagues. So yes, in general, the shapes of the features are the same, just flipped upside down, if you will, in emissivity versus reflectance. And the trends that we can see in for the band position MG number trends that we can see for the samples for which we have emissivity measurements are essentially equivalent to those that we see in the reflectance spectra.
Great, thank you. Well, let's thank our speakers one more time. This is a very interesting session with lots of great content. And I appreciate everyone's presentations and questions. We can see if you come up with questions later, you should be able to see the speakers' contact information on in their abstracts on the SSERVI website. So if there is nothing else, I think we can.
We should remind people that the poster session is tomorrow at 9:30 a.m. Pacific time. It's 9:30 Pacific time, I think, isn't it? I believe.
Yes. Cool. So let me just go to the schedule here, make sure. So Thursday, we have our poster session again, just like John said, at 9:30 a.m. Pacific time. So let's make sure we go see all the posters in the session as well for additional fantastic compositional sample analysis content. All right, well, thank you, everyone. Have a wonderful rest of your afternoon or evening or morning, depending on where you are.
Thanks, everyone.